Hello there, and welcome to Science for Sleep, a quiet place where questions soften at the edges and curiosity settles in like a warm blanket at the end of a long day. I'm glad you're here tonight, because we're about to drift into something that has puzzled scientists, thinkers, and pretty much anyone who has ever stared at the night sky and wondered how all of this holds together. You've probably heard the word spacetime 1,000 times, maybe in documentaries where the narrator speaks in that low hypnotic voice, maybe in books that try to explain it with grid diagrams that somehow made things more confusing, or maybe in conversations where someone confidently said they understood it and you had the sneaking suspicion they were guessing. It's one of those ideas that seems simple when you first hear it, but then the edges of it start stretching and curving until you feel like you're holding onto mist. And that's what makes it strangely comforting to talk about right before sleep. There's no pressure to solve it, only to wander through it slowly and let it unfold at its own pace. Before we sink into this, I'd love to know something small and personal, something grounding. Where are you listening from tonight? And what time does your clock say right now? It's funny how we're about to explore something that's supposed to weave the entire universe together, yet each of us arrives here from our own tiny corner of it. Some of us are settling into bed, some are halfway through a long night shift, and some are just taking a moment to unwind before giving sleep another try. Wherever you are, I'm glad you decided to join this little nighttime detour, and if you find these soft science wanderings helpful or soothing, or simply a nice companion for drifting off, it would mean a lot if you'd like the video or subscribe. It helps this gentle corner of the internet reach others who might need something quiet and steady to fall asleep to, but only if it feels right. For now, let's take a slow step into the question that brought us here. Why don't we understand space-time yet? Something that seems like it should be straightforward, because space is where everything goes and time is when everything happens, so when you put those together it ought to make sense. Except it doesn't. Not quite. Not fully. Not in a way that lets us say, yes, we've got this, the universe is tidy and cooperative. And maybe the reason the answer slips through our fingers is because we're still trying to wrap our minds around something that isn't shaped the way our minds expect. There's a moment that happens to most people the first time they hear the word space-time. It's a slight pause, as though the brain is trying to decide whether it's dealing with a math problem, a science fiction idea, or a philosophical puzzle. We grow up thinking of space as a vast emptiness, a backdrop, the place where stars hang and galaxies spin. And we think of time as a sequence, a flow, the hours ticking past. They feel separate because that's how we experience them. We stand in one place and the clock moves forward. Simple, but then you learn that space and time are not two things but one intertwined structure. And suddenly the simple picture tilts. It's no longer a canvas with events painted onto it. It's something flexible, something that bends, something that reacts to mass and energy. And that reaction is what becomes gravity, which is already strange when you think about it. We were all taught that gravity was a force that pulls things together. But in Einstein's picture, it isn't a pull at all, it's geometry. The shape of space-time telling objects how to move, and objects telling space-time how to curve. That alone is enough to make most people blink slowly. Even people who dedicate their lives to studying physics sometimes admit that they don't understand space-time in the way we usually define understanding. They can calculate it, they can predict how it behaves, they can write equations that match what we observe in the universe, but understanding something intuitively, with the ease of saying 2 and 2 make 4, that's a different story. Space-time refuses to fit neatly into our everyday experience because it doesn't care about our everyday experience. It operates on scales far larger and far smaller than anything we interact with. So when we try to grasp it, we're trying to use tools built for life at the human scale to interpret something decidedly not designed for the human scale. Imagine you're holding a sheet of fabric. You press your fist into the middle of it, and you see the dip it creates. If you roll a small ball across it, the ball curves around the dip as though it were being pulled. That's the classic visual explanation for curved space-time. It's a nice picture. Helpful, in a way. But it's also misleading because the sheet is sitting in a larger space. gravity in the demonstration is actually real gravity acting downward, not the simulated gravity of geometry. The image works as a metaphor, but the universe doesn't actually sit on a giant table with a giant force pulling down on it. Spacetime curves in a way that's difficult to visualize because it curves through itself, not into something else. Our brains don't naturally picture dimensions beyond the three we move through, so even the best metaphors fall a little short. That's where things start to feel slippery. If the metaphors don't fully match reality, and the equations don't translate cleanly into pictures we can carry in our heads, then understanding becomes something more like approximating. We get close, but we don't quite get there. And maybe that's why discussing spacetime feels like gently pressing into a mystery. It doesn't resist, it just keeps stretching. People often ask why the universe needs such a complicated structure in the first place. Why not simply separate space and time and keep things tidy? The truth is that nature doesn't seem particularly motivated by our desire for simplicity. The combined structure of space-time emerges naturally when you look at how light behaves, how objects move at high speeds, and how gravity influences everything. The speed of light becomes a sort of anchor. It stays the same no matter who measures it, and that stubborn speed forces space and time to adjust themselves around it. One observer might see two events happen at the same moment, while another moving at a different speed would disagree. Time becomes flexible, distances shrink or stretch depending on relative motion, and suddenly space and time can't operate as separate concepts anymore. They merge into something unified, something that accommodates the fact that different observers can experience reality differently without contradicting the laws of physics. The moment you accept that, something else follows. If space-time adjusts itself depending on motion, then the difference between space and time is not as absolute as it seems. They can mix, they can trade roles, time can behave differently in different conditions, space can stretch. And these distortions are not just theoretical, we measure them, we rely on them. GPS satellites, for example, experience time differently because they orbit farther from Earth's gravity and move at high speeds. Without correcting for those time differences, your phone's navigation would become hopelessly inaccurate within minutes. So even though space-time might feel abstract, its effects show up in familiar ways. Yet understanding it fully still remains elusive, because the very idea that time can run differently, or that space can stretch, is not the kind of thing our senses evolved to detect. Another reason we struggle with space-time is because it sits at the intersection of two major theories that don't play nicely together. On one side, there is general relativity, Einstein's geometric masterpiece that describes planets, stars, galaxies, and the universe at large. On the other side sits quantum mechanics, which handles the tiny scale, the level of particles, probabilities, and strange behaviours that seem to follow their own rules. Both theories work astonishingly well in their respective domains. But when you try to apply both at the same time, especially in places where space-time becomes extremely curved and extremely small, like the centre of a black hole or the first moments after the Big Bang, the two theories clash, the equations break, the predictions fall apart. It's as though the universe has two sets of instructions, both correct yet incompatible when they overlap. And space-time sits right at that uncomfortable boundary. This tension creates a sort of scientific limbo. We know space-time exists. We know it bends and stretches. We know it responds to mass and energy. But we do not know what it's made of, or if it's made of anything at all. Some physicists propose that space-time is smooth and continuous, like a perfect fabric. Others propose that it's granular, made of tiny discrete pieces too small to see. Some think it could be emergent, forming from something even more fundamental, something not yet discovered. In that sense, space-time might be like a mirage that appears when deeper structures interact in complex ways. Or maybe it's real in the most literal sense. We simply don't know, and that lack of certainty is part of the puzzle. Trying to understand space-time is also difficult because studying it requires experiments and observations that push technology to the extremes. It's easy to test physics in a lab when the distances are small and the forces are manageable. But when the subject of study is the structure of the entire universe, or how space bends around a black hole, the opportunities to gather data are sparse. We can't go to a black hole and measure its curvature directly. We infer things from the way stars move or from ripples in gravitational waves that travel across the cosmos. We build machines that measure tiny distortions in laser beams caused by gravitational waves passing through Earth. Those measurements tell us something about space-time, but only in the most delicate, indirect ways. It's like trying to understand the shape of a creature you've never seen by studying only the ripples it makes when it swims past you. The limits of perception, tools, and scale all contribute to the challenge. Our intuition is shaped by experiences close to home, on a planet where gravity feels constant, where time seems steady, and where distances don't usually stretch or bend. Space-time operates beyond those boundaries, so naturally it feels unfamiliar. The more we try to picture it, the more it slides away from familiar patterns. Even explaining it often requires comparisons to things it is not. We call it a fabric, but it isn't cloth. We describe it as a grid, but it isn't drawn. We imagine it stretching, but stretching implies a substance in a larger space, and space-time isn't inside anything else. It is the thing everything else is inside of. That mismatch between what it is and what we can easily imagine is one of the biggest barriers to understanding it. And yet, that difficulty is part of why people keep returning to the subject with a sense of wonder. Even if you can't see space-time directly, you can feel the edges of its influence. Every falling object, every orbit, every second ticking on your watch is shaped by it. We live within it constantly, even if we don't fully grasp its nature. And as we ease further into this long exploration, we'll keep unraveling why this strange union of space and time remains just out of reach, why scientists keep searching for clearer answers, and why the very structure we live inside still surprises us no matter how closely we study it, gently moving from one idea to the next as the night settles in a little deeper. There's something quietly fascinating about thinking of the universe as being held together by something you can't touch or see, something that never makes a sound and never sits still, yet manages to shape everything from the way planets orbit to the way your feet stay on the ground. When people talk about this strange structure, they often picture some kind of invisible sheet stretched under the cosmos, something smooth and steady that lies beneath everything. But the truth isn't quite that simple, because this structure isn't truly a sheet, and it definitely isn't steady. It bends, changes, stretches, and responds to everything around it, even the smallest shift in energy or mass. And the more you try to picture it, the more it seems to slip away, as though it's not really designed for the kind of imagination we use for ordinary things. If you think about your everyday life, everything seems solid and predictable. The floor stays flat. Gravity pulls downward rather than sideways or in some unexpected direction. A ball thrown across the room follows a path that feels familiar. You don't wake up wondering whether you'll slide off the bed because Earth suddenly bent the wrong way. Things stay in place. But that sense of stability is only the surface of what's really happening. Beneath the everyday view is a world shaped by a fabric that's constantly shifting, in quiet ways we never notice. To really sense how strange this structure is, imagine holding a piece of elastic cloth between your hands. If you press your finger into it, the cloth dips. If you stretch it, the pattern changes. But if you let it go, it tries to return to its original shape. This is a common comparison people use when they first hear about how space bends around mass, yet it doesn't quite capture what's going on. The cloth has a resting shape. It has a direction in which it sits. It depends on gravity pulling down on it. None of those things apply to space-time. The comparison works only in the most loose sense, a way to get your bearings before the real strangeness sets in. Because space-time isn't a material. It isn't stretched over anything. It doesn't sit inside a larger space. It doesn't sag or droop under a hidden force. It is the very stage on which everything else exists, and that means we don't have a good everyday object to compare it to. Even the word fabric feels like it oversimplifies things. A fabric is made of threads, tiny pieces woven together. If you look close enough, you can pull it apart. Space-time, as far as we know, doesn't behave like something built from small pieces, though to be fair, we haven't been able to test it at the tiniest scales where its true nature might be hiding something more complicated. Right now, our best experiments suggest that space-time is smooth, but our theories suggest that smoothness might be an illusion, and that hidden beneath that smoothness could be something much more intricate, something that only appears smooth because we're too far away from the smallest details. That tension is part of why this structure feels so hard to understand. On large scales, it acts like a smooth continuum, allowing planets, stars, and galaxies to trace graceful paths. On small scales, the rules of quantum mechanics step in, and smoothness becomes questionable. Things begin to fluctuate, jitter, and behave in ways that no classical fabric would ever allow. This conflict feeds into one of the biggest questions in physics. What really holds everything together when you zoom in far enough? Is space-time something continuous? Or is it more like a mosaic of tiny pieces flickering in and out of place? The truth is, we don't know, and that uncertainty sits at the heart of why space-time remains such a peculiar challenge. Another part of the mystery comes from the way space-time affects motion. When you're walking, you don't think about being guided by a curved landscape you can't see. You simply feel solid ground under your feet and move in whatever direction you choose. But everything you do, from the path you take to the time it takes you to get somewhere, is shaped by the curvature of space-time around Earth. If Earth were more massive, time here would run slower. Distances would subtly change. Your steps would cover different lengths depending on how strong the gravitational field was. You wouldn't feel any of that directly. It would all happen behind the scenes. That's why physicists often say gravity isn't something you feel. You only feel the effort required to stop yourself from falling deeper into a curved path. Our intuition, built from childhood as we watch objects fall and roll, doesn't prepare us for the idea that motion itself is the natural path through a curved geometry. If you toss something upward, you think gravity pulls it back down. But the deeper explanation is that space-time curves around Earth in such a way that any object left alone will follow a curved trajectory. The object isn't forced downward, it simply moves along the shape of the space-time it's travelling through, and the shape of that space-time curves back toward Earth. When you see it that way, gravity becomes something much subtler than a pull. It becomes a property of the environment itself, and the entire universe is filled with this environment. To understand why this is so hard for people to grasp, imagine trying to walk in a perfectly dark room. The floor might slope gently, but if you can't see the slope, you wouldn't think the floor is changing. You would simply feel yourself moving in unusual ways and assume it was your own doing. That's how motion works in a curved space-time. We can't see the curvature directly. We only see the results of moving through it. So the universe we experience is partly shaped by something invisible that never calls attention to itself, and that makes it hard for our intuition to catch up. Even describing space-time mathematically is challenging. Einstein's equations, which explain how curvature arises from mass and energy, are notoriously complex. They work, but they work in a way that's hard to translate into everyday thinking. The equations describe relationships between distances and times, but they do so using tensors, tools that can handle complicated interwoven directions. These tools allow physicists to calculate the geometry of space-time in any situation, whether near a star or inside a galaxy cluster. But knowing how to calculate something is not the same as understanding it intuitively. If someone asked why this geometry takes the shape it does, or what it's made from, or why mass curves space-time at all, those questions are still open. The equations give the how, but not the why. Part of what makes this even stranger is that space-time doesn't just respond to mass, it responds to energy, pressure, movement, and even the absence of matter. Empty space has properties. It isn't a blank background. It can expand, stretch and change even in places where there's nothing at all. The expansion of the universe is a clear example. Galaxies aren't drifting away because they're moving through space like boats on water. They're drifting apart because space-time itself is stretching, carrying them with it. That stretching doesn't need engines, forces or winds. It's a built-in behavior of space-time, which means the very emptiness between galaxies has structure and dynamics, even though it looks empty to us. And this leads to another difficulty. When we try to study something that doesn't behave like a substance and doesn't act like a force, we run into limitations. If you push on air, it moves. If you heat metal, it expands. If you stretch a rubber band, you can feel the resistance. But if you ask what happens when you stretch space-time, the answer is not so straightforward. Space-time doesn't resist. It doesn't exert a pressure that can be measured in the usual sense. It doesn't have a texture. It simply changes, and the only sign of that change is the movement of whatever sits inside it. This lack of direct interaction means we're always studying space-time indirectly, through the behavior of things moving through it. And studying something only through its effects is like trying to understand wind by watching leaves move. You see the consequences, but not the thing itself. Something else that complicates the picture is that space-time is dynamic. It's not a fixed container. It evolves, ripples, and interacts with the universe it holds. When two black holes merge, the collision sends ripples outward, stretching and compressing space as the waves move. We have detected these waves, and the measurements match what general relativity predicts. But observing something doesn't immediately make it intuitive. The idea that space itself can vibrate like this is very different from anything we experience directly. When a wave passes through Earth, changing distances by tiny amounts, nothing feels different. Your body doesn't sway. Your bed doesn't move. Yet the wave is real, altering the geometry around you for a brief moment. Trying to understand something you can't feel or see, yet is always present and active, is naturally hard. We aren't built to sense these things. Evolution didn't require us to understand cosmic scale geometry in order to survive. Our senses developed only to help us interact with surfaces, shapes, and distances in the world immediately around us. So when the universe turns out to operate on principles far beyond what we're equipped to detect, we end up needing mathematics, instruments, and imagination to fill the gap. Another challenge comes from the fact that space-time contains both space and time brings its own complications. Time is something we experience, but we don't experience it in a consistent way. It stretches and compresses depending on what we're doing. The fact that space-time weaves this uneven sense of time together with the geometry of the universe creates a structure that is difficult to visualize. If space were the only part, we could picture it as a shape. But when time becomes part of the structure, shape becomes an incomplete description. The geometry now changes depending on motion, perspective, and gravity. The result is a landscape where time can move differently for different people in different places, making the structure feel less like a fabric and more like a living map that adjusts itself for every observer. And all of this circles back to why we say space-time holds everything together. It doesn't hold things the way glue does, or the way a web traps whatever lands on it. Instead, it holds everything by setting the rules for how things move and how events unfold. The shape of space-time determines the paths that objects follow. The way time flows determines the order in which events happen. Together they make the universe coherent, even if the coherence is hidden beneath layers of complexity. What makes this structure so difficult to fully grasp is that we're used to thinking of things as either places we move through or clocks that measure change. Space-time is both at once, a place and a system, a map and a timeline, a geometry and a rhythm. Trying to blend those ideas into one picture is not something our minds naturally do. It becomes easier to see why this structure feels so mysterious. It's everywhere, it shapes everything, and yet it never directly reveals itself. And that quiet hiddenness is part of what makes exploring it feel like wandering through a puzzle that stretches out just beyond the edge of what our thoughts can comfortably grasp. It's always interesting to think about how certain ideas in science become familiar to us almost immediately, while others seem to drift just out of reach no matter how many times we hear them explained. Einstein's picture of space-time is one of those slippery ideas. You can hear it described dozens of ways, listen to countless videos about it, and still come away with a feeling that something didn't quite click. It's not a failure of imagination or intelligence, it's something built into the idea itself. Einstein reshaped the foundations of how we view the universe, but he did it in a way that doesn't line up with how our senses process the world. So even though the theory has been around for more than a century, most people still find it strange. And honestly, that reaction is natural. Part of the reason Einstein's idea feels so unfamiliar is that it asks us to rethink things we've been certain about since childhood. We grow up trusting that space is just a big, empty area where things sit, and time is a steady flow that moves forward whether we pay attention to it or not. These ideas come from everyday experience, not textbooks. You don't need to study physics to know that if you drop something, it falls straight down, or that if you start watching a movie at 8 o'clock, the next hour passes at the same rhythm it always does. Then suddenly Einstein comes along saying those simple assumptions aren't accurate, space isn't empty, time isn't steady, gravity isn't a force pulling objects downward, and both space and time can stretch, bend and warp depending on motion and mass. No matter how calmly someone explains it, that's a lot for the mind to absorb. Another challenge is that much of Einstein's theory doesn't align with the way humans evolved to interact with the world. Think about how your brain judges distances and times. When you walk across a room, your sense of space is straightforward. When you wait for something to happen, your sense of time is linear. But Einstein describes a world where space and time are interconnected and influenced by factors our senses can't detect. Nothing in our daily routine suggests that time runs differently at different heights, or that space curves in the presence of mass. So when we hear these ideas, our first instinct is to try to fit them into the mental framework we already have. Unfortunately, the old framework doesn't match the new one, and the mismatch makes Einstein's ideas feel like they belong to another reality altogether. Even something as simple as the speed of a light being constant in every situation is counterintuitive. If you throw a ball while standing still, it moves at one speed. If you throw it while running forward, it moves faster relative to someone watching. That's easy to grasp. But Einstein shows that light doesn't behave this way. No matter how fast you move, the speed of light remains exactly the same. And because the speed of light refuses to change, something else must change instead. That something ends up being space and time. Distances compress or stretch. Durations slow down or speed up. These adjustments keep the speed of light fixed, even though nothing else in our experience behaves like that. Trying to picture this leads to one of the first mental roadblocks. Most of the things we understand are based on patterns we've seen. When you stack blocks, you learn about solidity. When you pour water, you learn about flow. When you spin around too fast and feel dizzy, you learn about motion. Einstein's theory deals with conditions that our senses never directly encounter. We don't move at speeds close to light. We don't live around objects massive enough to make space-time curve in obvious ways. We don't experience time dilation or length contraction in daily life. So the theory has almost nothing in common with the patterns our brains rely on. Another reason Einstein's idea still feels unfamiliar is that the explanations we often hear are simplified metaphors. They are helpful but incomplete. You hear people talk about the fabric of space-time, or a rubber sheet with heavy balls placed on it, or clocks ticking differently depending on where they are. These comparisons can give a sense of what's happening, but they don't fully capture the deeper ideas. They can even make the concepts feel more confusing because they resemble things we understand, yet they behave differently. When something looks familiar but doesn't follow familiar rules, the brain doesn't quite know how to categorize it. Take the idea that time can slow down depending on how fast you move or how close you are to a massive object. You can listen to the explanation and nod along, but unless you've experienced it, it won't feel intuitive. And since none of us have travelled at speeds close to the speed of light or lived beside a black hole, our understanding remains theoretical. We can measure these effects using atomic clocks and satellites. We can prove they're real with experiments. But having evidence is different from having intuition. You can believe something fully without feeling it instinctively. Einstein's idea also challenges one of our strongest assumptions, that there is a universal now. It's comforting to think that at this very moment, everyone everywhere is experiencing the same point in time. We picture the world as synchronized, even though we know people live in different time zones. Einstein's theory breaks this assumption. What counts as now depends on your motion. Two people moving relative to each other can disagree about whether events happened at the same moment, not because one of them is wrong, but because simultaneity isn't absolute. This idea alone is enough to make people pause because it disrupts something very basic about how we perceive our place in the world. Another strange thing about Einstein's picture is that it doesn't tell you why space-time behaves the way it does. The equations show how mass and energy influence the curvature of space-time, and how that curvature influences motion, but the underlying mechanism is still unclear. It's like having a map that accurately shows the roads and intersections but doesn't tell you who built them, or why they take those specific shapes. You can describe space-time as geometry, but the question of what exactly is being curved remains open. That gap in understanding makes the theory feel incomplete on a fundamental level, even though it works perfectly for predictions. One more reason the idea feels unfamiliar is that the pictures used to visualize space-time curvature tend to be two-dimensional, even though the real structure is four-dimensional. When you see a diagram with a grid being pulled downward around a sphere, that grid is a stand-in for something much more complex. We look at the diagram and instinctively try to interpret it as we would interpret a drawing of hills or valleys. But the curve in space-time isn't a curve in a physical direction. It's a curve in the geometry itself. Our mind tries to imagine bending something without bending it into anything else, and that's not something we have prior experience with. The visualization is useful for calculating or demonstrating a principle, but it doesn't create true understanding. Another element that adds to the difficulty is that Einstein removed the need for forces in his explanation of gravity. Forces are easier to picture. If you push something, it moves. If you drop something, gravity pulls it downward. But Einstein says objects move along natural paths in curved space-time, and the sensation of gravity is really the sensation of resisting that natural motion. This flips the roles of cause and effect. Instead of gravity causing the curvature is gravity. It's not a force acting on an object, it's the shape of the environment guiding motion. When you try to explain motion using shapes instead of forces, the idea requires a shift in thinking that takes time to settle. Even people who dedicate decades to studying the theory admit that certain parts still feel conceptually strange. The math is clear, the predictions are verified, the theory works flawlessly in experiments. Yet many aspects remain difficult to internalize. It's like learning a new language late in life. You can become fluent, but sometimes your native language still feels more natural. For Einstein's theory, our native language is Newton's physics, the simple rules we grew up with. Those rules worked well enough for everyday life, so replacing them with something more complicated and less intuitive is naturally uncomfortable. Einstein's idea also feels unfamiliar because it implies that our perception of reality is limited. We like to believe our senses give us a complete picture of the world, but if space can bend and time can shift, and we can't detect those shifts without instruments, then our senses are only picking up part of the story. This realization can create a subtle sense of distance between everyday reality and deeper physical reality. That distance has a way of making the theory feel like something we observe from the outside rather than something we live within. There's also the fact that Einstein's work opened doors to questions that became even stranger. Black holes, gravitational waves, the expansion of the universe, singularities, the possibility that time could behave differently in extreme environments. Each of these ideas pushes the limits of what feels natural. So the unfamiliarity doesn't just come from the core theory, it also comes from everything the theory allows and predicts. When you follow the logic of curved space-time, you end up in places where intuition has almost nothing to guide it. And then there's the emotional aspect. When a theory challenges your sense of how the world works at the most basic level, it creates a disconnect. You can accept it intellectually while still feeling unsure about it internally. The theory becomes something you believe rather than something you grasp. That feeling isn't a flaw, it's simply part of the learning process. Space-time is enormous, dynamic, and mathematically complicated. Understanding it deeply requires both patience and a willingness to let go of familiar assumptions. Not everyone feels ready for that shift immediately, and that's okay. If you think back to the first time you heard about relativity, you might remember a moment where the explanation seemed straightforward. Then as you continued listening, it gradually became more complicated. That shift often happens because the first layer is simple. Objects move, time flows, the speed of light stays constant. But the deeper layers require a reorganization of how you picture the world. Instead of imagining fixed space and steady time, you have to imagine something flexible with rules that change depending on motion and gravity. The human mind likes categories. Einstein asks us to blend categories together. And despite all of this, something quietly remarkable happens once you become comfortable with not fully getting the idea. You start to appreciate the beauty of the structure, even if the structure doesn't entirely fit into your intuition. You realize that it's okay for an idea to be partly out of reach. Many of the most important discoveries in science started as things people didn't fully understand right away. The unfamiliarity isn't a barrier. It's a sign that you're dealing with something genuinely deep. There's a moment in the history of science where everything shifted. A point where the seemingly steady world people thought they understood gave way to something deeper, something far more flexible than anyone had suspected. For a long time, people believed the universe was built on fixed foundations. Space was the endless container holding stars and planets. Time was the universal rhythm that never changed its pace. The rules seemed simple. Objects moved. Clocks ticked. Everything unfolded within a stable stage. Then, little by little, evidence began to appear that the stage itself wasn't as rigid as it looked. What felt like an ordinary backdrop was behaving in ways no one had predicted. And that shift is what eventually led to the realization that space could bend and time could stretch. One way to see how surprising these ideas were is to imagine being alive before they existed. If you looked at the sky at that point in history, you saw a predictable pattern. The planets moved in smooth paths. The sun rose and set. Stars returned to the same positions year after year. There were mysteries, of course, but the overall picture looked steady enough that people assumed space and time must be steady as well. Even when scientists began developing detailed mathematical laws to describe motion, those laws assumed that distances and duration stayed the same, no matter where you were or how fast you moved. It seemed like common sense. Then more precise experiments began to disrupt that sense of stability. One of the first hints came from studying light itself. Light didn't behave the way anyone expected. When scientists tried to measure its speed, they kept finding the same number over and over, regardless of whether Earth was moving toward the light source, away from it, or sideways relative to it. This was strange because for every other kind of motion, speeds add or subtract depending on how you're moving. If you're running and throw a ball forward, the ball's speed is your speed plus the speed of the throw. But with light, no matter how fast you moved, the speed stayed the same. At first, some thought this meant measurements were flawed. Others thought perhaps the universe contained a hidden medium that carried light, something that would keep its speed fixed by design. But repeated experiments showed the same result. No medium was found. Light simply refused to change its speed. This puzzle left the scientific community in an uncomfortable place. The equations describing electricity and magnetism, which predicted the speed of light, had been tested extensively and worked extremely well. But those same equations implied a world where the speed of light was a constant for everyone. If those equations were right, then something else had to give. Either the nature of motion wasn't what people thought it was, or time and space weren't fixed the way people assumed. Most people at that time preferred to believe motion worked the same for everything. After all, that matched everyday experience. But the experiments didn't agree. Into this confusion stepped Einstein, who wasn't trying to be dramatic or revolutionary. He simply wanted the laws of physics to work the same for everyone, regardless of how they were moving. That seemed like a reasonable request. He didn't want different observers to have different laws. He wanted consistency. But in trying to preserve that consistency, he realized something surprising. For the laws to stay the same, space and time themselves would have to adjust. They wouldn't be separate. They would form a single interconnected structure that responded to motion. If one person moved quickly and another stayed still, they wouldn't measure time passing at the same rate. They wouldn't agree on distances in the same way. These differences weren't mistakes. They were built into the universe. This was the beginning of the idea that space could bend and time could stretch. But the idea didn't emerge all at once. It grew from many small steps. Einstein's early papers focused mainly on what happens when objects move at high speeds. He found that time slows down as speed increases. Lengths contract in the direction of motion. These effects weren't noticeable at everyday speeds, which is why people never saw them happening around them. But at speeds close to the speed of light, the changes became significant, and if speed could change the flow of time and the shape of space, then space and time weren't fixed at all. They were flexible. That alone was surprising enough. But the real moment when space began to bend in a literal sense came later, when Einstein thought about gravity again. He knew Newton's description of gravity worked well for most situations. Newton had said gravity was a force pulling objects toward each other. But Einstein wondered whether that picture was complete. If space and time changed with motion, maybe gravity wasn't a force at all. Maybe it was another expression of spacetime's flexibility. That line of thinking eventually led to a startling idea. Instead of seeing gravity as a pull, Einstein began to see it as the shape of spacetime itself. The insight came from a simple question. Why do objects fall? Newton would say they fall because gravity pulls them down. But Einstein considered another possibility. What if the object is actually following a straight path, and the path itself bends because space-time is curved? In other words, the object isn't being pulled, it's just travelling through a curved landscape. The curve guides its motion. This was a completely different way of looking at gravity. It made gravity less like a tug, and more like a path laid out by the geometry of space-time. To understand how radical this was, imagine you're rolling a ball across a floor. If the floor is flat, the ball travels straight. If the floor dips or slopes, the ball follows the curve. You don't need to push the ball downward. The shape of the surface determines the motion. Einstein realized that mass does something similar to space-time. It changes the shape around it, and everything inside that shape moves according to the geometry. That geometry is what we perceive as gravity. But unlike a floor, space-time isn't just a surface with a direction we can point to. It's the four-dimensional structure that includes both space and time, so when space-time curves, it doesn't just curve in a spatial sense. It curves in a way that changes how time flows and how distances behave. This is where the idea of stretching time becomes crucial. If space-time curves, then the flow of time itself can slow down or speed up depending on where you are and how strong the curvature is. Time becomes part of the geometry, not something separate. Think about standing on Earth's surface. You feel the weight of gravity. But Einstein would say what you're actually feeling is the resistance your body provides to avoid falling deeper into the curved path defined by space-time around Earth. Meanwhile, someone floating freely in orbit isn't feeling weight, because they're moving along a natural path determined by that same curvature. They're not escaping gravity, they're following it. They're moving through the curved space-time in a way that feels effortless. The idea that space could bend and time could stretch became clearer with specific predictions. For example, Einstein said that the stronger the gravitational field, the slower time runs. This wasn't metaphorical. It was meant literally. Clocks placed at different heights should tick at different speeds. Decades later, experiments confirmed this. Two clocks, one slightly higher than the other, ticked at rates that differed exactly the way Einstein predicted. This meant the stretching of time wasn't a mathematical curiosity, it was a physical fact. Another prediction was that massive objects would bend light. Since light travels through space-time, and space-time curves around massive objects, the path of light should bend as well. When astronomers observed starlight bending around the sun during an eclipse, the measurements matched Einstein's predictions. This wasn't the sort of bending that could be explained by refraction or atmospheric distortion. It was space-time shaping the path of light itself. The realization that the universe behaves this way changed how people viewed almost everything. Instead of seeing the universe as a collection of objects acting on one another through forces, Einstein revealed a universe where geometry plays a central role. That shift wasn't just a scientific adjustment, it changed the entire mental map people use to understand reality. When you discover that the very foundation of the universe bends and stretches, you have to reconsider what it means for something to move or for time to pass. But even though these ideas are mathematically precise and experimentally verified, they never fully settle into ordinary intuition. It's difficult to imagine time running slower, simply because you're standing closer to a massive object. It's difficult to visualize the curvature of space-time without picturing it as bending into some external space, even though that's not what's happening. And it's difficult to think of gravity not as a pull, but as a path laid out by geometry. Another challenge is that space-time doesn't always bend in gentle, gradual ways. Near extremely massive objects, the bending becomes intense. Black holes are the most dramatic example. At a black hole's edge, the curvature is so steep that not even light can escape the path it's drawn into. Time slows down so dramatically near this region that an outside observer would see the clock of a falling object freeze, even though that object would experience time normally. These predictions are not science fiction, they're direct consequences of space-time's flexibility, and observations increasingly support them. What makes it even more interesting is that space-time doesn't only bend around stars or planets, it bends around anything with energy. Movement, pressure, radiation, even empty space all contribute to the shape. The idea that empty space can have energy and influence curvature wasn't immediately obvious. But observations of the universe's expansion show that something in the empty regions appears to be pushing space outward. Whatever this phenomenon is, it's another sign that space-time is much more than a passive container. Thinking about all of this reveals why space bending and time stretching feel so different from the world we encounter daily. In everyday life, distances and durations feel stable, but Einstein's picture shows they're only stable under ordinary conditions, and even then only approximately. The real rules are more flexible. The flexibility remains hidden because our motion is slow, our gravitational environment is moderate, and we don't have instruments in our bodies capable of detecting tiny shifts in space-time. That hiddenness makes the whole structure feel mysterious, yet the bending and stretching aren't strange from the universe's point of view. They're simply how things work. The universe doesn't privilege our intuition. It operates on principles that remain consistent whether or not they feel natural to us. And it's that consistency that allows us to study these effects, measure them, and build an increasingly detailed picture of how space-time behaves, even if the picture doesn't quite match the way our minds naturally try to visualize it. There's a certain comfort in imagining that once we understand a big idea, the smaller details will naturally fall into place, as though the universe is just waiting for us to connect the dots. But when it comes to space-time, the opposite seems to happen. The more pieces we collect, the more we notice that many of them don't quite lock together the way we hoped. Some line up almost perfectly, some sit close but leave small gaps, others fit smoothly on one side but clash violently on another. And the more we examine these mismatched pieces, the clearer it becomes that understanding space-time isn't just a matter of adding new information. It's a matter of figuring out why the pieces aren't cooperating and whether we're even looking at them the right way. One of the most obvious mismatches shows up in the relationship between the universe on a large scale and the universe on a small scale. Einstein's theory does an extraordinary job explaining how things behave when they're massive and spread out, like planets, stars, and galaxies. It predicts the bending of starlight, the shifting of time in gravitational fields, the movement of galaxies, and even the ripples produced by black hole collisions. When astronomers measure these things, the results consistently follow the predictions. That's an impressive achievement, and it's part of why his work became one of the pillars of modern physics. But the smaller scale is ruled by something entirely different. Quantum mechanics governs atoms, particles, fields, and all the strange behaviors that happen in the microscopic world. Instead of smooth curves and continuous geometry, quantum mechanics deals with probabilities, fluctuations, jumps, and uncertainties. It doesn't describe motion the same way relativity does, it doesn't treat time the same way, and it doesn't treat space the same way. While relativity says space-time is a smooth, continuous structure, quantum mechanics suggests that nothing is truly continuous. Every field fluctuates, every position has uncertainty, every event has probabilities attached to it. If space-time were just another physical field, quantum mechanics would suggest it should fluctuate too. It should jitter, ripple, or break into tiny units. But at the scales we can measure, space-time appears calm and smooth, not jittery or grainy. This creates a tension between what the two major theories predict. Relativity demands comforting smoothness. Quantum mechanics demands restless motion. These demands can't both be right in all situations. Something must give. The mismatch becomes especially noticeable when you look at places in the universe where both theories should apply at once. Black holes are the clearest example. At the center of a black hole, relativity says the curvature of space-time becomes infinite. Everything collapses into a region with no volume at all. This is called a singularity. The equations break down there, not because the math is incomplete, but because the predictions become nonsensical. Dividing by zero, infinite density, infinite curvature, infinite something or other that no physical process can handle. Relativity wasn't designed to deal with infinities like that. It signals that it has taken itself as far as it can go. Quantum mechanics, meanwhile, doesn't allow infinities either. It insists that quantities remain finite and that the universe has limits on what can be squeezed or stretched. So when you ask what happens at the very center of a black hole, the two theories argue. Relativity predicts a singularity. Quantum mechanics predicts something else entirely. But neither theory can take over completely because both are essential near a black hole's core. The mismatch leaves a void in our understanding, a place where the pieces don't fit and the picture becomes blurry. A similar problem arises when studying the very beginning of the universe. According to the best models, the universe started in a state of extremely high density and temperature. Relativity can roll the clock backward and describe the expansion of the universe until the numbers get too extreme. Then the equations fail, pointing again toward a singularity. But that singularity isn't a physical object. It's a sign that the theory isn't equipped for the job. Quantum mechanics should be able to help because the early universe was tiny, and tiny things fall under its domain. But quantum mechanics also fails when gravity becomes overwhelmingly strong. The two theories don't cooperate. They talk past each other like two experts from different fields, who both know they're right but can't agree on a common language. This incompatibility creates an uncomfortable feeling. We have two incredibly successful descriptions of nature, both verified by countless experiments, and yet they can't be merged smoothly. It's like owning two excellent maps that overlap but don't connect at the edges. Each one is reliable on its own, but when you try to place them together, the roads don't line up. The rivers bend in different places, the borders don't match, and that's unsettling because a complete understanding of space-time requires a map that covers everything without contradictions. The universe doesn't divide itself neatly into the large and the small. The same reality must obey a single consistent set of rules, even if we haven't found them yet. Another piece that doesn't quite fit comes from trying to understand what actually causes space-time to bend. Relativity says mass and energy shape the geometry, but that explanation doesn't reveal the underlying mechanism. Why does mass cause curvature? Why does energy distort the geometry around it? Why does space-time respond at all? The equations show how curvature behaves. They don't explain why the relationship exists. This leaves a gap. It suggests that space-time's behavior may be more fundamental than relativity describes. Something deeper might be influencing the geometry, something we haven't identified. Then there's the question of whether space-time is truly smooth, or whether it only appears that way at the scales we can observe. Some theories suggest that space-time might be made of tiny discrete units, much smaller than atoms, smaller than any particle we've ever detected. If space-time had a granular structure, it would mean the smooth geometry of relativity is only an approximation, not a complete description. But if it does have such a structure, our tools aren't sensitive enough to detect it. We can't confirm or deny it. That uncertainty creates another mismatch, a place where the pieces remain ambiguous. Emergent space-time is another idea that floats around in the world of theoretical physics. According to this idea, space-time might not be fundamental at all. Instead, it might arise from deeper physical processes the way temperature arises from atoms in motion. A single atom doesn't have a temperature, but a large collection of atoms does. Similarly, the universe might contain some underlying ingredients that produce space-time when combined in large numbers. If that's true, then space-time itself might not exist at the smallest scales. It might show up only when enough of the underlying components interact in a particular way. This idea is intriguing, but it leaves us with puzzles. If space-time emerges from something else, what is the something else? How does it produce geometry? And why does the resulting geometry behave the way it does? Another puzzle piece that doesn't fit cleanly involves something called vacuum energy. Quantum mechanics predicts that empty space is never truly empty. It's filled with fluctuations, tiny bursts of energy appearing and disappearing constantly. When physicists calculate how much energy these fluctuations should create, the number they get is staggeringly large, far too large to match what we observe in the actual universe. The predicted value and the real measured value differ by an amount so enormous that it's often called the biggest mismatch in the history of physics. Relativity says energy affects curvature. If empty space contained as much energy as quantum mechanics predicts, the universe would curl up instantly or expand at an unbelievable rate. But neither of those things happen. The observed universe expands at a perfectly manageable pace. This means the calculated vacuum energy must be wrong, or relativity's relationship between energy and curvature must be incomplete, or both. Another example of two puzzle pieces refusing to click together. Dark energy offers another mismatch. Observations show that the universe is expanding faster over time, not slower. Relativity allows for this behavior if you include a term in the equations that acts like a repulsive energy spread through space. But no one knows what this energy is. We can measure its effects, we can describe the way it works mathematically, but we don't understand the origin or the mechanism. It behaves like a property of space-time itself, something built into the geometry. But it doesn't fit with quantum predictions, and it doesn't match anything we've seen in experiments. It sits uneasily between theories, as though pointing toward a missing piece we haven't recognized. Dark matter creates a different sort of mismatch. Galaxies spin faster than they should if all the mass inside them were visible. Stars at the edges move so quickly that based on visible mass alone, they should fly away into space. But they don't. Something unseen provides extra gravitational pull. The simplest explanation is that there's invisible matter we haven't identified. But no particle we've predicted or discovered fits the behavior perfectly. Relativity explains how the invisible mass shapes the geometry, but the nature of the mass remains unknown. Another puzzle piece with no clear home. A more subtle mismatch comes from the role of time. In relativity, time is woven into space-time and treated as a dimension. But in quantum mechanics, time isn't treated the same way. It doesn't become part of a unified geometry. Instead, it remains an external parameter, a backdrop against which events unfold. This creates tension. How can time be part of space-time in one theory, but a separate parameter in another? The two pictures don't align, and until they do, any unified picture remains incomplete. Even the way forces behave is divided. Relativity describes gravity not as a force but as a geometric effect. Quantum mechanics, meanwhile, describes all other forces using particles and fields. Gravity doesn't fit into this framework cleanly. Attempts to treat gravity as a quantum force run into contradictions. Trying to describe space-time as a field on top of a fixed background doesn't work because space-time is the background. Trying to quantize the geometry leads to mathematical results that blow up or collapse. Each approach reveals useful insights, but ultimately runs into walls that signal something missing. These walls aren't failures. They're clues. They show us that the pieces we're working with belong to a larger puzzle, whose outline isn't fully known. Another mismatch appears when you look at the concept of locality. Relativity insists that nothing can influence anything else faster than the speed of light. Quantum mechanics, on the other hand, allows entangled particles to appear correlated instantly across distances. These correlations don't transmit useful information faster than light, so relativity isn't technically violated, but the deeper explanation remains unclear. Does space-time allow this instant matching of states because it has some structure we don't understand? Or do the correlations hint at something that lies outside space-time altogether? All of these mismatches create an unusual kind of tension in physics. We have a clear picture on large scales and a clear picture on small scales, but the two pictures don't merge into one. They stand next to each other, accurate within their own domains, yet unable to overlap smoothly. That tension makes space-time feel unfinished, as though we're working with a set of tools designed for different jobs that haven't yet been combined into a complete toolkit. And rather than discouraging scientists, these mismatch pieces have encouraged deeper exploration. Each gap, contradiction, or unexplained result points towards something new waiting to be discovered. It's hard not to feel a certain curiosity when thinking about how the universe behaves at its smallest scales, especially after spending so much time with the more gradual curves and smooth structures of space-time. When everything is large enough to see, or even large enough to imagine without effort, the world feels steady. It makes sense that planets orbit, that objects fall, that light follows predictable paths, and that time moves forward in a controlled rhythm. But when you shrink the picture down to the tiniest regions, past atoms and into the realm where particles flicker in and out of existence, all that steadiness falls away. The rules you thought you knew stop applying. Patterns break, certainties dissolve, and instead of behaving like orderly pieces in a grand cosmic machine, the components of the universe act like they're following instructions written in a language that doesn't quite match anything else. This shift from the smooth structure of space-time to the restless behavior of quantum rules is one of the main reasons the pieces of the cosmic puzzle never quite fit together. The two sides of physics describe the same universe, yet they speak entirely different dialects. On one side, space-time bends and stretches predictably. On the other, particles jump, fluctuate, and ignore many of the expectations we bring with us from everyday experience. It's almost as if the universe uses a different playbook when it's looking at the microscopic scale, and it doesn't bother explaining what changed. Trying to make those two perspectives align is like trying to solve a puzzle whose pieces reshape themselves whenever you glance away. One of the first surprises that emerges when you look closely at quantum behavior is that particles don't seem to have definite positions until you measure them. In everyday life, objects stay where you put them. A cup doesn't smear itself across the counter just because you're not looking at it. But at the quantum level, particles don't sit still in fixed, predictable places. They spread out into probability clouds that describe where they're likely to be. And until something interacts with them, there's no single location you can assign. The universe doesn't treat position as a fixed attribute. It treats it as a shifting range of possibilities. This leads to one of the earliest lessons you encounter in quantum mechanics: the idea of uncertainty. Not uncertainty in the sense of, we're not sure because we haven't looked hard enough, but uncertainty built into the structure of the universe itself. The more precisely you try to measure a particle's position, the less precisely you can know its momentum. The reverse is equally true. It's not a matter of using better instruments. The limitation is woven into the fabric of the quantum world. This behavior stands in sharp contrast to relativity, which describes things in terms of smooth geometries and continuous paths. There's no uncertainty in the bending of space-time. Everything follows a clear trajectory, determined by the curvature. But in the quantum world, trajectories dissolve, paths blur. The concept of a definite track becomes something the mathematics can't provide. This creates an immediate conflict with the expectations set by space-time. Another strange rule arises from the way particles behave as both waves and particles at the same time. If you send particles like electrons or photons through a pair of slits, they create an interference pattern, the kind you would normally associate with waves spreading and overlapping. But if you try to observe which slit each particle passes through, the interference disappears and the particles behave individually instead. The simple act of observing changes the result. This isn't because the observer is doing anything dramatic. It's because the rules of the quantum world involve probabilities that only collapse into a definite outcome when measurements occur. Before that moment, the possibilities remain spread out, coexisting in a way that has no counterpart in the larger world. This dual nature is hard to reconcile with the smooth geometry of space-time. Space-time doesn't decide which path an object takes only after someone looks. It doesn't have categories that shift depending on observation. It's built on predictable relationships between mass, energy, and curvature. But quantum mechanics isn't built that way. It's built on probabilities, wave functions, and sudden changes that have no equivalent in relativity. The universe doesn't seem bothered by the inconsistency, but humans have a harder time with it. Trying to imagine something that behaves like a particle and a wave simultaneously stretches intuition past its usual limits. Another frustrating aspect of quantum rules is the way particles can become entangled. When two particles become linked through a quantum interaction, their states remain connected regardless of how far apart they move. If you measure one particle, the other instantly reflects a matching result. There's no signal travelling between them that we can detect. The connection doesn't weaken with distance, it simply remains. This seems to violate one of the most cherished principles of relativity. Nothing can influence anything else faster than the speed of light. Yet quantum entanglement does something that looks suspiciously like faster-than-light influence, even though it doesn't technically transmit information. It creates a kind of correlation that's impossible to explain using only the smooth rules of space-time. This mismatch leads to a deeper question. Does entanglement occur within space-time, or does it operate outside of space-time altogether? If it occurs within space-time, then its instant connections don't make sense. If it occurs outside of space-time, then what does outside even mean? Does the universe contain a deeper structure that underlies space-time and allows these correlations to happen? Or does space-time fail to describe the universe at the quantum level, meaning its rules apply only on larger scales? These questions don't have clear answers yet. They sit between theories, pointing toward gaps we haven't found a way to bridge. The quantum world also behaves in ways that seem unnecessarily restless. Even in a perfect vacuum, where no particles should exist, quantum fields fluctuate. These fluctuations cause tiny bursts of energy to appear and disappear constantly. It's as if the empty regions of the universe never sit still, even for a moment. Relativity describes empty space as a smooth background that can bend and stretch, but it doesn't include the restless jitteriness that quantum mechanics predicts. And when physicists try to calculate how much energy those fluctuations should add to the vacuum, the result is far too large. If the quantum prediction were right in full detail, space-time would curve so dramatically that the universe would collapse or expand uncontrollably. But that doesn't happen, so something must be off, either in the calculations or in the assumptions behind them. Another place where the quantum rules refuse to behave nicely is in their treatment of time. Relativity treats time as part of the geometry of space-time, a dimension shaped by mass and motion. Time flows differently depending on where you are and how fast you're moving. It's dynamic and flexible. But in quantum mechanics, time plays a very different role. It acts as a fixed parameter, something that ticks forward at a uniform rate for all systems, regardless of the forces or conditions involved. There are no time loops or shifts or curves in the basic equations. Time doesn't stretch or bend, it stays put. This difference creates a major conflict. If time is part of space-time and space-time curves, then time should curve too. But quantum mechanics doesn't allow its version of time to curve. It doesn't even treat time as something that can respond to forces or geometry. That mismatch leaves physicists with equations that work extremely well, but don't match each other at a fundamental level. Another challenge appears when trying to combine gravity with quantum rules. Every other force in the universe can be described using particles that carry the force. Photons for electromagnetism, gluons for the strong force, and so on. If gravity were like these forces, it would have a particle called the graviton. But trying to describe gravity using a graviton leads to mathematical problems. The calculations blow up into infinities that can't be removed or simplified. This suggests that gravity doesn't fit into the quantum framework the same way the other forces do. It behaves more like geometry than like a field. But if gravity is geometry, how can it be quantized? How can the shape of space-time itself become probabilistic or uncertain? The attempt to answer these questions has led to numerous theories, each with its own set of assumptions, but none have been proven correct. Even the idea of a particle raises questions when you look at it too closely. In quantum field theory, particles aren't tiny, solid objects. They're excitations of underlying fields. An electron isn't a miniature sphere, it's a ripple in the electron field. A photon is a ripple in the electromagnetic field. These ripples follow quantum rules, and they can overlap, vanish, or reappear in ways that don't resemble how objects behave in daily life. But if particles are ripples, what does that make space-time? Is it a field too? If so, what kind of field? And how does that field ripple? These questions circle back to the earlier mismatch between smooth geometry and quantum uncertainty. Ripples in space-time would be gravitational waves, and those have been detected. But the waves behave differently from other field excitations. They're incredibly weak, gentle compared to the restless fluctuations predicted by quantum mechanics. It's unclear whether the two pictures can be reconciled. Another odd rule emerges when considering how quantum mechanics treats measurement. In relativity, measurement is straightforward. You measure distances, times, or velocities, and the values follow the geometry. But in quantum mechanics, measurement changes the system being measured. The wave function, which describes the probabilities, collapses into a definite outcome. Before the collapse, the system behaves as a superposition of possible states. After the collapse, it behaves like a classical object. No one knows why this collapse happens or what exactly triggers it. Some theories suggest it's a physical process. Others suggest it's an informational update. Some propose that collapse never happens and that all outcomes exist in parallel. But none of these explanations fit smoothly into the geometric picture of spacetime. If measurement changes the system, does spacetime play a role in the collapse? Does collapse affect the curvature of spacetime? If so, how? The theories don't agree. Another curious aspect is how quantum mechanics treats motion. In relativity, motion follows clear paths called geodesics. But in quantum mechanics, motion becomes a matter of probabilities. Particles don't travel from point A to point B on a single path. They take all possible paths, and the probabilities interfere to produce the final outcome. This picture is radically different from the smooth curves of space-time. Trying to merge these perspectives creates contradictions. If a particle takes all paths, does it sample all possible curvatures of space-time along the way? Does space-time shape the probabilities, or do the probabilities shape the curvature? These questions sit at the intersection of two incompatible theories. Even the vacuum behaves differently in the quantum picture. In relativity, empty space is neutral. In quantum mechanics, empty space is never empty. It seethes with temporary particles that appear and vanish. If space-time were fully compatible with quantum rules, this seething should affect curvature dramatically. But it doesn't. Something keeps the quantum fluctuations from dominating space-time, even though the theory says they should. The lack of agreement between prediction and observation is one of the biggest mismatches in all of physics. Another rule that refuses to behave comes from the idea that quantum systems don't have definite properties until they're measured. In relativity, objects carry their properties with them regardless of who observes them or how. But in quantum mechanics, the act of observation creates definite properties where none existed before. This introduces an observer-dependent element into the theory that relativity doesn't include. Relativity insists that physics must be the same for all observers. Quantum mechanics suggests that observers play a role in shaping the outcome. These views can't be easily reconciled. Each of these strange rules contributes to the sense that quantum mechanics, while accurate in its predictions, behaves like it belongs to a different universe entirely. And yet it describes the same reality we live in. That mismatch, that refusal of the quantum world to align itself neatly with the rules of space-time, creates a tension that won't go away. It pushes physicists to search for a deeper theory that might unify these behaviors, a theory that explains why the quantum world behaves so differently and why space-time behaves so smoothly. There's something quietly puzzling about gravity when you sit with it long enough. It's one of the first things we learn to recognize long before we know the word for it. You feel it every time you drop something, every time you stand up, every time you watch an object fall. It's familiar in a way that almost nothing else in physics is. You don't have to explain gravity to a small child for them to know that things fall downward. It's built into everyday experience, woven into each moment without needing any attention at all. And because it's so ordinary, it's easy to forget how mysterious it really is, especially when you compare it to the other forces and behaviors that shape the universe. Gravity has a softness to it, a quiet influence that feels gentle next to the sudden jumps and unpredictable patterns of the quantum world. Yet despite its familiarity, gravity is the one area where our understanding reaches a hard limit, faster than almost anywhere else. One of the first things that makes gravity so strange is how incredibly weak it is compared to other forces. It's strong enough to keep you anchored to the floor, strong enough to shape planets and stars, strong enough to control the structure of galaxies, yet the amount of mass needed to produce those effects is enormous. If you compare gravity with something like electromagnetism, the difference becomes almost unbelievable. A small magnet on your refrigerator can easily overpower the gravity of an entire planet when it pulls a piece of metal upward. That means the force holding that little piece of metal to the fridge is stronger than the force Earth exerts on it. Somehow, the force that shapes the entire cosmos is weaker than something sitting quietly on your kitchen appliance. This mismatch in strength leads to an uncomfortable question. If gravity is so weak, Why does it dominate the large-scale behaviour of the universe? The answer lies partly in the fact that gravity always attracts. Other forces can push or pull, cancel out, or reverse direction. Gravity only accumulates. Every bit of mass adds to the total pull. There's no negative mass to counteract it. This means that even though gravity is weak on small scales, it becomes incredibly significant when large amounts of mass collect. But the deeper question still remains. Why does gravity behave so differently from everything else? Why is it so gentle compared to the other forces? And if it's a completely different kind of interaction, is that why it refuses to merge smoothly with quantum rules? Another thing that makes gravity feel mysterious is the way it acts on everything equally. Electromagnetism applies only to charged particles. The strong and weak forces act only inside atoms. But gravity applies to anything with mass or energy. It doesn't care what the object is made of. It doesn't care whether it's charged or neutral. It doesn't care whether it's sitting still or moving. It acts consistently on every physical thing. This universality is part of what led Einstein to the idea that gravity might not be a force at all, but a feature of space-time. If something affects everything the same way, maybe it's baked into the structure of reality. Maybe it doesn't push or pull. Maybe it simply shapes the paths things naturally follow. Einstein's view of gravity as curved space-time worked brilliantly for explaining many observations, but it also created new questions. If gravity isn't a force, then what is the underlying nature of this curvature? What does it mean for space-time to bend? Why should mass cause curvature in the first place? The equations describe the relationship with great accuracy, but they don't reveal the mechanism. It's a bit like having a perfectly reliable set of instructions for how something behaves, while still not knowing what the object itself is made of. You can predict it, you can measure it, you can confirm its effects, but you can't quite say what it really is. One of the clearest places where the limits of our understanding show themselves is inside black holes. These objects form when matter collapses under its own gravity, to the point where nothing can escape, not even light. Einstein's equations predict exactly how black holes distort space-time near their edges. They describe how objects would fall into them, how light would bend around them, how time would slow near them. All of that matches observations, but the equations break down when you try to describe what happens at the very centre. The curvature becomes infinite, and quantities that should stay finite explode into impossible values. This breakdown isn't a sign that the universe falls apart at that point. It's a sign that our understanding does. Gravity pushes our theories into regions where they stop working. It's almost as if the universe quietly tells us, "You've gone as far as these tools can take you. Something else is needed from here onward." And no matter how hard physicists try to refine the equations, the singularity remains a reminder that the story of gravity isn't finished. Another area where gravity tests our limits is in the behaviour of the universe as a whole. When astronomers predicted how galaxies should rotate based on the gravity of the visible matter inside them, the results didn't match the observations. The edges of galaxies were rotating much faster than they should have been. Instead of slowing down with distance, their rotation curves stayed flat. Gravity was stronger than the visible matter could explain. The simplest explanation was that there must be more mass than we can see, something invisible but heavy enough to create the additional pull. That idea became known as dark matter, but decades later, no one knows what dark matter is. It hasn't been detected in a laboratory, it doesn't emit light, it doesn't interact with electromagnetism, it shapes galaxies, yet refuses to reveal itself in any direct way. This leaves gravity acting as a messenger for something we don't understand. It shows us the effects but hides the source. A similar problem appears with dark energy. Observations show that the universe is expanding, and not only expanding but accelerating. Something is pushing space-time apart. Something with negative pressure, something that causes expansion rather than contraction. Again, gravity is the messenger. It shows that space-time is stretching faster than it should, but it doesn't tell us why. The equations can accommodate this behavior by adding a term, but the origin of that term remains unknown. So gravity creates curves and stretches that point to phenomena we don't understand. It highlights patterns but withholds explanations. These puzzles become even more challenging when we try to connect gravity with quantum mechanics. Quantum mechanics describes the behavior of particles and fields with extraordinary accuracy. Gravity describes the behavior of space-time equally well on large scales. Both theories are pillars of modern physics, yet they don't merge. Attempts to combine them lead to contradictions. In quantum mechanics, forces are carried by particles, but treating gravity as a force carried by particles leads to mathematical explosions that can't be resolved. In relativity, gravity isn't a force carried by anything, it's the shape of space-time. But trying to describe space-time as something quantized doesn't match smoothly with the existing framework of quantum field theory. Each approach works beautifully on its own, but they refuse to behave when brought together. This is where the nature of gravity creates one of the biggest tensions in physics. If gravity is geometry, then the quantum behavior of particles must take place inside that geometry. But if space-time itself becomes uncertain at small scales, then the geometry must also be affected by quantum rules, which means gravity should be quantized too. But each attempt to quantize it leads to inconsistencies that don't arise with the other forces. It's almost as if gravity sits at the edge of both theories, touching each one but belonging fully to neither. One reason this problem is so hard is that gravity doesn't shield itself. Other forces have ways of weakening or cancelling out. Electromagnetism can be neutralized by opposite charges. The strong force is confined to tiny regions inside atoms, but gravity extends everywhere. It cannot be blocked or isolated. You can't create a region where gravity is turned off to study it in isolation. You can't shield an experiment from gravitational influence the way you can shield it from electromagnetic fields. Gravity's reach prevents us from separating it from the rest of reality, which makes it extremely difficult to study under controlled conditions. That lack of isolation is part of why the deeper nature of gravity remains hidden. Another problem is that gravity becomes much stronger relative to other forces only at incredibly high energies or in extremely dense regions. The quantum effects of gravity would show up at energy scales far beyond anything we can achieve with current technology. The universe doesn't give us many opportunities to observe gravity in those extreme environments either. Black holes provide one, but their centers are hidden behind event horizons. The early universe provides another, but we can't directly observe the first tiny fraction of a second after the Big Bang. So the conditions where gravity and quantum mechanics collide are precisely the conditions we cannot access experimentally. That lack of direct evidence leaves theorists working with mathematics, looking for a structure that brings everything together without contradicting known physics. Another subtle difficulty lies in the way gravity defines the stage on which all physical processes happen. Quantum mechanics assumes a fixed background, a stage that doesn't change. But gravity refuses to provide such a stage. It curves the background. It changes the distances, the timing, the geometry. It shapes everything, including the stage itself. Trying to place quantum rules on a stage that constantly changes leads to calculations that spiral into impossible values. This creates a circular problem. Quantum mechanics needs a fixed spacetime to function smoothly. Gravity insists that spacetime is never fixed. Even the simplest question, such as what happens at the exact point where a particle interacts gravitationally with spacetime, becomes tangled. Does the particle create a ripple in spacetime? Does the ripple have a quantum nature? Are these ripples smooth or grainy? Does the geometry itself fluctuate? How do these fluctuations interact with the particle's own fluctuations? Each question branches into new ones, and each branch reveals more gaps in our understanding. These limits aren't signs that physics is failing. They're signs that physics hasn't reached the full picture yet. They show the edges of our current framework, and gravity is one of the main places where those edges become obvious. It doesn't resist being understood. It simply reveals its complexity slowly, piece by piece, as though encouraging us to look more closely. What makes this even more interesting is that gravity doesn't behave differently out of stubbornness. It behaves differently because it's tied to the fundamental shape of the universe. Everything that happens in the cosmos depends on the geometry created by gravity. The structure of galaxies, the behavior of planets, the bending of light, the expansion of the universe, the slowing of time near massive objects, the patterns formed by matter and energy, all of these things follow the quiet influence of gravity. Yet gravity remains the least understood of all the major interactions. There's a peculiar kind of tension that appears when you try to make sense of the universe from two completely different angles. On one side, there's the world of massive things, the realm where galaxies stretch across unimaginable distances and stars burn for billions of years. On the other side, there's the world of the tiny, where particles flicker, jitter, and swap identities in less time than it takes to blink. Each side has its own rules, its own language, its own sense of logic, and in a strange way, each side behaves beautifully on its own. The large-scale universe follows the predictable curves of space-time. The small-scale universe follows the restless dance of quantum mechanics. Neither side seems particularly bothered by the other until you try to bring them together. That's when the arguments start. It feels a bit like listening to two people describe the same story from completely different viewpoints, both convinced they have the correct version. The large-scale description relies on smooth shapes and gradual shifts. The small-scale description relies on probabilities and sudden jumps. If the universe behaved like one or the other, things would be simpler. But reality insists on using both at the same time, and that insistence creates a set of problems that have kept scientists puzzled for decades. A natural place to start is with the fact that space-time, as described by Einstein, is continuous. It curves gently around massive objects. It stretches during cosmic expansion. It creates the paths that planets follow, and the timing differences we measure with precise clocks. Everything about it suggests a smooth structure, something you could, in theory, zoom into endlessly without encountering individual pieces. But the quantum world doesn't believe in smoothness. It insists on uncertainty. It insists on fluctuations. It insists that nothing can be perfectly still or perfectly defined, no matter how small you go. This difference in how each side sees the universe creates an immediate conflict. If space-time is smooth, then the paths particles follow should also be smooth. But quantum mechanics says particles don't follow well-defined paths. They smear out into a range of possibilities. They can be in two places at once in a probabilistic sense. They don't move along tidy curves. They follow patterns that only become clear when you look at them statistically. So if you try to describe a particle moving through curved space-time, you end up trying to force these contradictory views to cooperate. The smooth curvature of relativity doesn't blend easily with the fuzzy probabilities of quantum mechanics. Another conflict shows up when you examine how each theory treats energy and motion. In relativity, energy is tied directly to the curvature of space-time. More energy means more curvature. The relationship is clear and consistent, but in quantum mechanics, energy fluctuates constantly, even in empty space. These fluctuations happen at such high frequencies and short timescales that they would create dramatic curvature if relativity treated them the same way it treats ordinary energy. But they don't create dramatic curvature. If they did, the universe would be wildly unstable. So one theory says energy fluctuation should reshape space-time. The other theory says those fluctuations are unavoidable. Yet when you compare the two predictions, they contradict each other. Something has to be missing from the picture. The mismatch becomes even more obvious when you try to describe gravity on the smallest possible scales. If you shrink your viewpoint down to a space far smaller than an atom, The curvature predicted by relativity becomes uncertain due to quantum fluctuations. Distances blur. Time blurs. Even the geometry itself becomes something you can't pin down. But relativity relies on precise geometry. If the geometry becomes uncertain, the equations fall apart. Trying to use relativity in a region controlled by quantum rules is like trying to draw a perfect circle on a surface that won't stop shaking. No matter how carefully you try, the picture collapses into noise. At the same time, if you try to use quantum mechanics to describe gravity, things become equally difficult. Quantum mechanics treats forces using particles. If you want to describe electromagnetism, you use photons. If you want to describe the strong force, you use gluons. Following that logic, gravity should be carried by a particle too. The hypothetical particle is called the graviton. But when physicists try to build a theory using gravitons, the math quickly becomes unmanageable. The calculations produce numbers that grow without bound. The infinities become impossible to remove. It's a sign that gravity doesn't behave like a normal quantum force. These difficulties reveal something important. The large-scale behavior of the universe is governed by geometry. The small-scale behavior is governed by probabilities, and the rules for each are built in ways that don't translate smoothly. One deals with smooth curves, the other deals with fluctuations. One assumes certainty in the structure of space-time, the other strips certainty away. Each works beautifully within its own domain, but neither one can fully describe the regions that lie between. Another place where this conflict becomes apparent is at the beginning of the universe. If you follow the expansion backward, you reach a point where everything was compressed into an incredibly small region. That region was tiny enough to require quantum mechanics, yet dense enough to require relativity. Both theories should be essential there. But when you use relativity to describe that moment, it predicts a singularity with infinite density. When you use quantum mechanics, the mathematics refuses to accept infinity. The two theories argue with each other so strongly that neither one can provide a clear answer. The earliest point in cosmic history remains hidden, not because of a lack of data, but because our theoretical tools can't reconcile the large and the small. A similar clash appears at the center of black holes. The outer regions can be described using relativity. The curvature is intense but manageable. But as you approach the center, the density becomes enormous. Quantum effects should take over. Yet relativity continues predicting curvature that becomes infinite. Quantum mechanics insists that infinities cannot be physically meaningful. The two theories reach a standoff, each unable to describe the region fully. This is another sign that the universe doesn't operate on a single unified set of rules. At least not the set of rules we currently understand. Even the way quantum mechanics handles space and time creates conflict. In relativity, space and time are woven together. They stretch and bend based on motion and gravity. They're flexible. But in quantum mechanics, the equations assume space and time form a stable background. The particles change, the fields fluctuate, but the stage remains steady. This is essential for many of the calculations that quantum theory relies on. But it directly contradicts relativity, which says the stage is never steady. It curves and shifts constantly. Trying to force quantum rules onto a shifting stage leads to equations that refuse to behave. The conflict becomes even clearer when examining what happens when particles try to probe very small distances. In quantum mechanics, the more precisely you try to measure position, the more uncertain momentum becomes. That means that probing a very tiny region requires high energy. But high energy creates curvature in space-time. The more you try to see, the more you distort the very thing you're trying to measure. If you push hard enough, the energy used to probe the region becomes large enough to create a tiny black hole. That black hole hides the region from view entirely. In other words, the act of trying to observe the small-scale structure of space-time prevents you from seeing it. This is one of the clearest signs of how incompatible the two theories are in extreme regimes. Another tension arises from the way quantum mechanics handles information. In quantum theory, Information about the state of a system is preserved over time. It might become spread out or scrambled, but it remains. In relativity, black holes seem to destroy information. If something falls into a black hole, its information appears to vanish from the universe. That disappearance would violate quantum principles. This created a long-standing puzzle often called the information paradox. Efforts to solve it have led to new ideas, but no solution has been universally accepted. Once again, the conflict between the large and the small creates a gap in understanding. Then there's the behavior of particles themselves. In quantum mechanics, particles can tunnel through barriers. They can shift from one state to another through interactions that don't match any classical intuition. They behave in superpositions. They don't settle into definite states until measured. But relativity describes particles moving along definite paths shaped by geometry. There is no room in relativity for superpositions of paths. There is no room for tunneling through barriers shaped by continuous curvature. You can try to adjust the equations to allow for probabilistic motion, but the geometric framework resists it. The very structure of relativity demands that objects have defined positions and paths, but quantum mechanics refuses to give them. Even the basic idea of space breaks down differently in each theory. In relativity, space is part of a four-dimensional geometry. In quantum mechanics, space is an arena where fields operate, but it doesn't have inherent curvature unless gravity enters the picture. And when gravity does enter, the quantum description becomes unstable. Space doesn't behave the same way in each theory. Time doesn't behave the same way either. In relativity, time depends on motion and gravity. In quantum mechanics, time is a parameter that stays uniform. This mismatch is one of the deepest obstacles preventing the large and the small from working together. Another problem comes from how each theory handles vacuum energy. Quantum mechanics predicts enormous vacuum energy. Relativity predicts that energy curves space-time. Yet the actual curvature of empty space is tiny. The two predictions differ by a factor so large that many physicists consider it the biggest failure in theoretical physics. The fact that the universe doesn't curve violently is strong evidence that one or both theories must be incomplete in their current form. Another subtle conflict shows up in how each theory approaches cause and effect. Relativity demands that cause precede effect and that nothing happens faster than the speed of light. But quantum entanglement creates correlations that appear instant. While these correlations can't transmit information, their existence challenges the strict causal structure that relativity relies on. If two particles can share a state instantly across vast distances, does that mean space-time structure isn't the full story? Or does it mean quantum mechanics operates through a deeper layer of reality that relativity doesn't describe? All of these mismatches point toward a simple but unsettling conclusion. The universe doesn't present a unified picture when studied through these two frameworks. The large ignores the small's preferences. The small ignores the large's geometry. Each side insists on its own rules, and neither one has room for the other's behavior. It's almost as if the universe is showing us two partial images and waiting for us to realize that the full picture requires a viewpoint we haven't developed yet. It's surprisingly easy to forget that whenever scientists talk about measuring the universe, they're not just measuring the things inside it. They're measuring within something that never sits still, never stays uniform, never truly behaves like a fixed backdrop. When you're trying to figure out how space-time works, you quickly run into the uncomfortable fact that the stage you're standing on is constantly shifting beneath your feet. And the more precisely you try to measure it, the more complicated that shifting becomes. It's like trying to understand the layout of a room while someone is quietly rearranging the furniture one piece at a time. Each measurement makes sense on its own, but when you compare one measurement to another, the changes become impossible to ignore. People often imagine science happening on stable ground. They picture rulers, clocks, test benches, and experiments carefully laid out in neat arrangements. The mental image includes a steady background, a kind of universal reference frame where everything stays put. But in the real universe, nothing stays put. Space stretches, time slows or speeds depending on where you are. Distances shift depending on motion and gravity. Even the emptiness of space changes over time. This makes the act of measurement far more subtle than it appears. You're always trying to measure something using tools that are themselves influenced by the very thing you're measuring. A good starting point is the idea that any measurement of distance or time depends on the stability of the measuring tool. A ruler must keep the same length, a clock must keep the same pace. But in space-time, neither of those assumptions holds perfectly. Distances depend on how space curves. Time depends on how gravity and motion affect the flow of events. If you move quickly relative to someone else, your ruler appears shorter to them. Your clock ticks more slowly. From your perspective, everything seems normal, but from theirs, everything has changed. Both viewpoints are correct. There is no single, universal stage everyone shares. This becomes even stranger when you realize that every attempt to measure space-time uses space-time itself as part of the measuring process. When you send a beam of light from one point to another, the path it takes depends on the curvature. When you measure time with a clock, the rate it ticks depends on how gravity shapes the flow of time where the clock sits. You can't step outside space-time to observe it from a distance. You're always observing from within, always subject to its shifts. That makes the whole process fundamentally tricky. One of the most famous examples of this difficulty came from attempts to detect a substance once believed to fill the universe called the ether. Scientists thought light might travel through this medium the way sound travels through air. If that were true, Earth would move through the ether, creating a detectable difference in the speed of light depending on direction. But experiments showed no difference at all. No matter which direction you pointed your measuring device, the speed of light remained constant. The stage refused to reveal any preferred direction or stable medium. Instead, it revealed something deeper. It showed that the structure of space-time adjusts itself, so that the speed of light is the same for every observer, no matter their motion. This was one of the first clues that the stage was not fixed. Once Einstein stepped in with the idea that space-time itself adjusts to keep the speed of light constant, everything about measurement changed. It meant you couldn't assume distances were the same for everyone. It meant clocks wouldn't tick at universal rates. It meant that even the basic definitions of length and time depended on your motion and your gravitational environment. This flexibility created a new set of obstacles for scientists. If your tools change depending on your motion, how do you compare measurements? If time itself stretches and contracts, what does it mean for two events to happen simultaneously? The answers depended entirely on the frame of reference, and no frame had priority. Another difficulty appears when trying to measure distances in a curved space-time. In a flat space, you can stretch a measuring tape and expect it to give the same answer no matter where you use it. But in curved space, the path you choose affects the outcome. 2 points might be separated by one distance along one path and a slightly different distance along another. The curvature makes every measurement path dependent, and since the curvature itself depends on mass and energy, the environment is constantly reshaping the stage you're trying to map. Even something as simple as measuring time becomes complicated when space-time moves. If you place two identical clocks in different gravitational environments, they won't stay synchronized. One will tick slightly faster or slower than the other, depending on how space-time is curved around them. These differences aren't theoretical, they're measured regularly. GPS satellites carry extremely precise clocks that tick at a different rate than clocks on Earth's surface. Without adjusting for this difference, your navigation would drift dramatically. So even our everyday technology has to account for the fact that the stage is moving unevenly. The deeper problem arises from the fact that any attempt to measure space-time at incredibly small scales introduces quantum effects that make the stage even more unstable. To measure something precisely, you need high energy. But high energy distorts space-time. The measuring process affects the very thing you're trying to examine. At large scales, these distortions are too small to matter, At tiny scales, they become impossible to ignore. If you try to measure an extremely small distance, the energy required becomes so large that you risk creating a tiny black hole. This destroys the measurement completely. It's as if the universe has placed a guardrail around the smallest possible scales, preventing you from examining them directly. The act of looking too closely collapses the thing you were trying to see. This problem sits right at the intersection of relativity and quantum mechanics. Relativity treats space-time as a smooth, continuous surface. Quantum mechanics insists that uncertainty dominates small scales. When you try to combine these perspectives, the stage flickers and shifts in ways that neither theory can fully describe. Relativity can't handle fluctuations. Quantum mechanics can't handle geometry, so the stage becomes something that refuses to be fully measured by either framework. Another challenge shows up when considering cosmology. The universe is expanding, which means the distances between galaxies grow over time. If you try to measure the size of the universe, the result depends on when you measure it, how fast the expansion is happening, and which model of its geometry you use. The stage isn't just moving under you, it's stretching in every direction. You're trying to measure something that changes while you're measuring it. Even the idea of measuring distance becomes complicated because light takes time to travel. The object you're observing might be billions of years old, and the space between you and it has stretched during that time. So the measurement becomes a tangle of what distance even means. This leads naturally to the idea that the universe has no fixed frame of reference. There is no absolute backdrop, no special place where time ticks normally, no neutral ground where everything behaves nicely. Every location, every speed, every gravitational environment creates its own version of time and space, and each version is correct from its own viewpoint. This relativity of perspectives makes measurement a delicate process. You always have to specify the frame. You always have to specify the conditions, otherwise the measurements become meaningless. Another layer of complication arises when you consider gravitational waves. These are ripples in space-time that stretch and compress space as they pass through. If you're trying to measure distances with extreme precision, these ripples become important. They literally change the length of the objects you're using to measure. When observatories like LIGO detect gravitational waves, they use laser beams to measure tiny changes in distance between mirrors. But the waves don't just move the mirrors, they move the space between them. The entire measuring apparatus shifts along with the thing being measured. Yet because the stretching and squeezing occur in specific patterns, scientists can extract meaningful data. Even so, the process reveals how unstable the stage becomes when something dramatic happens in the universe. Another subtlety appears when considering the expansion of space. If you place 2 points far apart, the space between them grows. This doesn't require the points to move through space. It's the space itself that stretches. If you try to measure the speed at which the points are separating, the answer depends on how you choose to define the coordinates. In some coordinate systems, the points might appear to move faster than light. In others, they don't. The speed becomes a matter of definition rather than a physical velocity. This flexibility shows how bizarre measurement becomes when the whole stage is in motion. Even defining the concept of a straight line becomes challenging. In curved space-time, straight lines are paths that minimize distance. But because distances depend on the curvature, those paths bend even though they're considered straight within the geometry. They're called geodesics. They're the paths objects naturally follow when no other forces act. But measuring these paths requires knowing the curvature, and knowing the curvature requires measuring the paths. Each step depends on the other. It becomes a circular process where measurement and theory intertwine. Another complication is the way measurement tools themselves respond to gravity. Rulers made of physical materials stretch or contract depending on their environment. Clocks slow down in deeper gravitational wells. Instruments designed to be precise become subject to the very effects they're trying to measure. If you place a clock near a massive object, it ticks more slowly than one farther away. But the clock can't tell you it's ticking slowly. It behaves normally in its own frame. Only when you compare it to another clock does the difference appear. This means measurement often relies on comparing different regions of space-time, and those comparisons can't be made without accounting for the geometry. Another interesting issue arises from the simple fact that motion itself is relative. If you try to measure the stage while moving through it, your rulers contract and your clock slow. If you try to measure the stage while standing still, stillness becomes a matter of perspective. Someone else might see you moving. You can only measure the stage from your own frame, and your frame might not reflect the deeper structure. This makes interpretation as important as the measurement itself. These challenges become more severe when we try to explore theories that go beyond relativity. Some proposed theories suggest that space-time might be emergent, forming from deeper structures that don't resemble geometry at all. If space-time isn't fundamental, then measuring it becomes even stranger. You'd be measuring something that arises from something else, like trying to measure the smoothness of water while ignoring the molecules that create it. Every measurement would give a macroscopic view without revealing the microscopic details. The stage would be a secondary effect, not the primary reality. And as all of these difficulties accumulate, a larger question naturally forms. If the stage is always moving, always changing, always dependent on perspective, how can anyone claim to understand it fully? The answer might be that understanding doesn't come from trying to freeze the stage into a fixed shape. It comes from learning how the movement works. It comes from accepting that measurement in space-time is never simple, never detached, never independent of the thing being measured. Every observation is part of the structure. Every measurement sits within the geometry. It becomes harder to think of space-time as a simple stage once you start looking at how geometry behaves in the universe. At first glance, geometry feels like one of the most stable ideas anyone ever invented. It brings to mind straight lines, perfect circles, triangles that always add up to the same number of degrees. None of those shapes drift or breathe or slide around depending on the moment. They stay put. When you learned about geometry for the first time, it probably seemed like a calm, reliable subject that never changed its mind. But the universe doesn't treat geometry the way a math textbook does. Once you add gravity, motion, energy, and the flexibility of space-time into the mix, geometry stops being a quiet collection of shapes and becomes something much more dynamic. It responds, adapts, warps, and stretches. It acts less like a rigid set of rules and more like a living system that rearranges itself whenever something enters its environment. The idea that geometry might behave like this isn't intuitive because our everyday experiences don't show it directly. You don't walk across your living room and feel the floor bending under your footsteps. You don't see your walls curving when someone walks by. You don't feel time changing its pace depending on where you stand. Everything near you feels stable, and stability encourages the belief that geometry is fixed. So the notion that the shape of space itself can change strikes most people as odd. Yet this is exactly what Einstein showed. What he described wasn't just a geometric trick. It was a deep shift in how the universe handles structure. One way to sense this difference is to imagine placing a heavy object on a flexible surface. The surface bends downward, and anything rolling across it changes direction because of the bending. The rolling objects aren't being pulled, they're simply following the shape beneath them. This is the picture people often use to illustrate how space-time curves, and even though it isn't perfect, it does reveal something important. It shows that geometry isn't fixed, it reacts, it adjusts itself to what's present. But the real universe takes that idea much further because space-time bends not into another space, like the stretchy sheet in the demonstration, but within itself. It's not a surface resting on something larger, it's the entire structure in which everything exists. When that structure changes shape, nothing can escape its influence because there's no outside for anything to exit into. Once you accept that geometry can change, the next surprise is how much it can change. If you add mass to a region of space, the geometry bends inward. If you remove mass, it becomes flatter. If the universe expands, the geometry stretches. If gravity becomes intense near a compact object, the bending deepens dramatically. If two massive objects move around each other, the curvature interacts, creating ripples that travel outward. Suddenly, geometry starts looking less like a quiet diagram and more like something that responds with a kind of fluidity, the way water changes shape depending on whatever moves through it. These changes aren't optional, they're required by the laws of physics. When an object moves, it influences the geometry. When energy flows, the geometry shifts. When pressure builds up inside a star, the geometry around it adjusts accordingly. Even empty space has geometry built into it, so geometry becomes something that evolves, something that never stays frozen in time. You can almost think of it as a record of everything that's happening in the universe, constantly updated by the presence and motion of matter and energy. It's especially striking when you consider how sensitive space-time is to mass. The Earth curves space-time enough to keep the Moon orbiting. The Sun curves space-time enough to hold the planets in their smooth paths. Massive stars curve space-time so strongly that light itself bends as it passes by, and black holes curve it so deeply that the geometry closes in on itself. Each of these examples shows that geometry isn't a passive property. It reacts to what surrounds it, shaping the movement of everything within it. The way planets orbit isn't just a matter of pulling and pushing, it's the result of geometry telling objects how to move. The term telling might sound metaphorical, but it describes the idea well. When space-time curves, it changes the set of paths objects naturally follow. These paths are called geodesics, and they represent what happens when nothing interferes. If you toss an object into the air and let it fall, it's following a geodesic. If light from a distant star bends around a galaxy, it's following a geodesic. You don't need a force to guide these paths. The geometry guides them. In this way, geometry becomes an active part of the universe rather than a static picture. One of the most fascinating aspects of this behavior is that geometry responds instantly to mass and energy. That doesn't mean changes propagate faster than light, but it does mean that the presence of matter creates curvature right where it is. It's a bit like seeing the surface of water dip the moment you drop something into it. The response is immediate in the local sense. What travels outward are the changes in that curvature, the ripples of adjustment that take time to move across space. These ripples are gravitational waves, and they reveal another way geometry behaves like something alive. When massive objects accelerate, the curvature of space-time vibrates. Those vibrations spread across the universe, carrying information about the motion that created them. When scientists first detected gravitational waves, it confirmed more than just a prediction. It showed that the geometry of space-time isn't quiet. It can shake, oscillate, and ring the way a drum or a string vibrates after being struck. Except the instrument in this case is everything. Entire regions of space stretch and compress in alternating patterns as waves move through them. The amount of stretching is tiny for waves that reach us, but the fact that geometry itself vibrates at all is remarkable. It means that space-time isn't a rigid framework. It's elastic, responsive, and capable of carrying its own form of motion. This elasticity becomes even more striking if you think about the universe as a whole. Over cosmic time, the universe has expanded dramatically. The expansion isn't an explosion into an empty area, it's the stretching of space-time itself. Galaxies move away from each other not because they're flying through space, but because the space between them increases. This behavior again signals that geometry doesn't sit still. It grows, stretches, and evolves. There's no fixed shape for the universe. It's something that changes with time, influenced by whatever conditions were present earlier. When the geometry of space-time becomes dynamic, it raises a subtle point. If geometry is always changing, then measurement becomes more complicated than it seems. You're not measuring distances in a neutral environment. You're measuring them in an environment that responds to everything you're doing. Even the act of looking at geometry requires geometry to provide the path for light to travel. So understanding the shape of space-time becomes an interactive process, something that depends on the very thing you're trying to understand. This is especially clear near extremely dense objects. Near a neutron star or a black hole, the curvature becomes so steep that time itself slows dramatically. If geometry were passive, time wouldn't change its speed. But in curved space-time, the flow of time depends on the geometry. A clock near a massive object runs slower. A clock farther away runs faster. That means time isn't something separate from geometry. It's part of the same structure. When the geometry bends, the passage of time bends with it. People sometimes imagine that time slowing near a massive object means that the clock is running poorly. But the clock is functioning perfectly from its own viewpoint. It is space-time that's different. The curvature changes the rate at which moments pass. This behaviour affects everything equally. It doesn't matter if the clock is digital or mechanical or atomic. They all adjust to the same slower rate. That universality is one of the reasons gravity behaves unlike any other influence. It acts on everything equally because it's not acting on things, it's acting on geometry. This dynamic geometry also challenges the idea that the universe follows fixed rules written in a single consistent way. If the geometry changes, then the rules governing motion change too, not in the sense that the laws themselves change, but in the sense that the environment in which those laws operate shifts. If you were to remove all mass from the universe, the geometry would flatten. If you were to add enormous amounts of mass, the geometry would curve dramatically. The rules for how objects move stay the same, but the results look different because the stage isn't stable. This flexibility of geometry becomes even more interesting when you consider that geometry can store information. If two massive bodies orbit each other for millions of years, they shape the surrounding curvature in a way that reflects their motion. When they merge, the resulting gravitational waves carry that information outward. The waves don't just show that something happened, they reveal exactly how it happened. The shape of the waves contains data about the masses, their speeds, their spins, and the final object they form. That's not something you expect from geometry if you're thinking of it as a static idea. That's something you expect from a physical medium or a field. It suggests that geometry behaves more like a participant than a background. Another way geometry shows its dynamic nature is through the influence of energy. Energy doesn't have to be in the form of mass to curve space-time. Light curves space-time too. Radiation curves space-time. Pressure curves space-time. This means geometry listens to more than just matter. It listens to anything that carries energy. In the early universe, radiation was abundant, and its presence played a role in shaping the geometry. This is part of why the universe evolved the way it did. The geometry wasn't responding only to matter, it was responding to energy everywhere. Then there's the question of whether geometry is fundamental or emergent. Some theories propose that space-time is made of something deeper, something we haven't identified yet. If that's true, then its dynamic nature could be a sign that geometry is a large-scale effect that arises from smaller interactions. In that case, the living quality of geometry might be a reflection of an underlying system behaving collectively. It would be similar to how temperature arises from the motion of particles. No single particle has temperature, but a group of them does. Geometry might work the same way. No single microscopic component would have curvature, but a large system of them could create curvature collectively. If geometry is emergent, then its responsiveness might make perfect sense. It wouldn't be a rigid structure. It would be the result of countless interactions working together, always adjusting to new conditions. This idea is still speculative, but it does show how far the concept of geometry has drifted from the simple shapes of early mathematics. It has become something richer, something that behaves like a system in motion, something that records the state of the universe while continually adjusting to it. There's a particular kind of quiet that surrounds the objects sitting at the far extremes of what we understand. That quiet isn't the kind you get from lack of information. It's the quiet you feel when you're standing near something that contains more answers than you know how to ask for. Black holes in the edges of the observable universe fall into that category. They're not just strange, they're places where the familiar rules begin to stretch, bend, and eventually stop cooperating. And in that misbehaviour, they reveal clues about space-time that don't appear anywhere else. They show us the parts of the universe where our theories reach their limits, where the math we trust starts whispering that something is missing. Black holes are especially good at exposing those limits because they make gravity so intense that space-time curves in ways that challenge every assumption we usually rely on. If you picture a star much larger than the Sun collapsing under its own weight, the gravity eventually becomes strong enough that nothing can escape it, not even light. From the outside, you can still describe the gravitational field, the rotation, the temperature of the surrounding material, and the radiation emitted as matter spirals inward. Those pieces follow the equations of relativity with remarkable precision. Yet the closer you get to the centre, the more the equations push towards something they weren't built to handle. At the very core of a black hole, according to relativity, the curvature of space-time becomes infinite. It's not just a steep drop. It is a point where the equations stop providing meaningful answers. That point is called a singularity, and it represents more than a location. It's the place where the mathematics breaks down so completely that it becomes clear something deeper is missing from our understanding. Singularities aren't physical in the usual sense. They're warning signs. They tell us that the model we're using has reached its limit. Relativity can describe the outside of a black hole beautifully. It just can't describe the inside in a complete way. Quantum mechanics doesn't help much at first glance. If you treat the inside of a black hole using quantum rules, you end up with contradictions that are just as severe. Quantum theory doesn't allow infinite densities. It doesn't allow space-time to collapse into a point. But relativity insists that's exactly what happens. The two theories disagree so strongly that they can't both be right in that environment. And since black holes are part of the universe, they force the question of what replaces the singularity once the missing theory comes into view. Another clue hiding in black holes appears when you think about what happens to information. If something falls into a black hole, its details seem to vanish from the universe once it crosses the event horizon. The event horizon is the boundary beyond which nothing can return. From the outside, you have no way to know what fell in. You can't see whether it was a rock, a gas cloud, or an entire star. All of the specific information seems lost, but in quantum mechanics, information must be preserved. It can transform, spread, or become nearly impossible to recover, but it cannot be destroyed. This principle is built into the framework of quantum theory. So when you place quantum mechanics next to black holes, another contradiction forms. The black hole seems to erase information. Quantum mechanics says that cannot happen. This disagreement led to the famous information paradox. It's one of the clearest examples of how black holes reveal gaps in our understanding of space-time. Einstein's theory predicts that information disappears. Quantum mechanics predicts that it doesn't. Both systems have been tested thoroughly. Both describe enormous swathes of the universe with incredible accuracy. Yet they cannot agree about something as fundamental as whether the universe loses information. This paradox has pushed scientists to explore new ideas, including the possibility that the information might not truly vanish, but instead be encoded in the surface of the event horizon or released back into the universe in a subtle way through radiation. That radiation, often called Hawking radiation, adds another layer of complexity. According to quantum mechanics, black holes aren't perfectly black. Virtual particles appearing near the event horizon can lead to the black hole slowly losing mass. Over incredibly long periods, the black hole evaporates. This evaporation process suggests that black holes have a temperature, which is something relativity alone does not predict. It also means that black holes can disappear over time, but if they evaporate entirely, what happens to the information trapped inside? Does it evaporate too? Does it leak out? Does it become encoded in the radiation? No one has solved the puzzle completely, but the existence of the puzzle itself reveals that black holes carry hints about the nature of space-time that we haven't yet deciphered. Black holes also challenge our understanding of space and time in a simpler but equally puzzling way. As you fall into a black hole, the geometry shifts around you so drastically that time and space behave in unfamiliar ways. From the viewpoint of an outside observer, you appear to slow down as you approach the event horizon. They never see you cross it. They see your motion freeze, your light becoming dimmer and stretched. But from your viewpoint, time moves normally. You cross the horizon without noticing anything unusual. This disagreement isn't an illusion. It's a natural consequence of the geometry. It shows how deeply tied our experience of time is to the curvature around us. And black holes amplify this reality to an extreme degree. Their edges reveal something subtle about space-time too. The event horizon isn't just a surface. It's a boundary where the idea of distance becomes deeply dependent on perspective. For someone falling in, the horizon isn't a special location. But for someone watching from far away, the horizon marks the limit of visibility. It's a surface defined not by physical material but by the structure of space-time itself. That makes it a geometric boundary, a place where the usual relationships between inside and outside break down. Understanding that boundary requires understanding how space-time organizes itself under extreme curvature. Another place where clues hide is at the very edge of the observable universe. When you look outward, the light you see from distant galaxies has been traveling for billions of years. The universe has expanded while that light traveled toward you, stretching the wavelengths and creating the redshift that astronomers measure. But the light only reveals part of the story. Beyond a certain distance, galaxies are moving away faster than light due to the expansion of space. That means their light will never reach us. The edge of the observable universe isn't a physical edge. It's a limit created by the speed of light and the expansion of space-time. And the fact that this limit exists tells us that space-time behaves in ways that relate directly to energy, pressure, and the curvature of the universe. The expansion also raises the question of what lies beyond what we can observe. If space-time stretches faster than light can cross it, then there are regions we will never see. They exist, but they are forever beyond our observational reach. Those regions are cosmic edges too, not because space ends, but because our ability to see them does. These edges reveal how limited our viewpoint is, and how much of the universe remains inaccessible. They also force us to consider whether the geometry of space-time changes in regions we cannot observe, and whether the rules we infer from our visible patch represent the full picture. The early universe provides clues of its own. When you look at the faint microwave radiation left over from the early cosmos, you see tiny temperature variations spread across the sky. These variations give insight into the density fluctuations that later became galaxies and clusters, but they also reveal patterns that hint at the shape of space-time itself. Some versions of cosmology suggest that the universe might be flat. Others suggest it might have a slight curvature. The fact that the cosmic microwave background shows such uniformity in opposite directions of the sky, despite those regions never having been in contact early on, led to the proposal of cosmic inflation. Inflation is a rapid expansion that smoothed out irregularities and stretched space-time dramatically. It's another example of geometry acting dynamically and revealing clues through its behavior. The edges of the universe's birth carry hints that space-time might have been shaped by processes that no longer occur. They hint at conditions where quantum mechanics and relativity both mattered. They also suggest that the structure of space-time might have been influenced by forces or fields that no longer dominate. These early edges provide a natural laboratory for understanding how geometry behaves under extreme conditions. But they also reveal how limited our tools are for peering into those conditions. The light that reaches us from the early universe has been stretched and dimmed by billions of years of expansion. It provides clues, but the clues are faint and incomplete. Another clue comes from the accelerating expansion of the universe. Something is causing space-time to stretch faster over time. This behavior suggests that space-time contains a form of energy with negative pressure, often called dark energy. But no one knows what dark energy is. It behaves like a property of the vacuum. It shapes the geometry on the larger scales, yet it doesn't interact with matter in any noticeable way except through gravity. That behavior indicates that something about spacetime itself contains energy we don't understand. The fact that this energy shapes the entire universe tells us that the geometry we see is only part of the story. Dark energy also raises the question of whether spacetime is stable or evolving towards some long-term state. If the expansion continues to accelerate, the universe could become increasingly isolated, with galaxies drifting so far apart that light from one cannot reach another. This would create new cosmic edges. These edges wouldn't be physical barriers, they would be boundaries created by the geometry and the expansion. The shape of space-time would determine what could communicate with what, and the expansion would dictate how the large-scale structure changes over time. Another clue comes from how black holes and cosmic edges might be connected. Some theories propose that the surface of a black hole, the event horizon, might behave like a two-dimensional system encoding the information about everything that has fallen inside. This idea extends beyond black holes. Some versions of cosmology propose that the entire universe might have a similar encoding on a distant surface. If that's true, then the geometry of black holes might provide hints about the geometry of the universe as a whole. The behavior of horizons might be a key to understanding space-time more deeply. As scientists continue to explore black holes, new questions appear. When two black holes merge, the gravitational waves carry information about the curvature that existed during the collision. Those waves contain subtle details that might reveal whether the geometry behaves differently than expected in extreme regions. Every new detection adds another piece to the puzzle, another glimpse into the edges of spacetime where the theories strain against their limits. And as the universe continues to expand, the cosmic edges drift farther away, creating a changing boundary of what we can see. This boundary isn't fixed, it moves as spacetime stretches. The behavior of that boundary offers clues about how geometry evolves. The fact that we can only study a finite region doesn't stop us from inferring the presence of structures that lie beyond it, but those inferences depend heavily on the assumptions we make about geometry. The farther we look, the more we rely on theories that might themselves be incomplete. All of these clues, scattered across black holes and cosmic edges, point toward the same idea. The universe contains places where our current understanding falters, where relativity and quantum mechanics collide, where geometry becomes too strange for our tools to handle. These places aren't just curiosities, they're guideposts. They show us where to look next. They show us where the boundaries of knowledge sit, and they prepare us for the next areas of inquiry just outside our current reach, letting the exploration continue onward. There's a certain challenge that appears when you try to make sense of something the universe refuses to display directly. Many parts of physics feel approachable, because they let you see what's going on, either with your eyes or with instruments that extend what eyes can do. You can watch a pendulum swing, you can track the motion of planets, you can record the spectra of stars. All of those things give you information in ways that feel accessible, even if the underlying explanations are complicated. But there are regions of reality where nothing is visible, nothing cooperative, nothing willing to reveal itself in the usual ways. You're left trying to understand phenomena that never show you their full picture, and sometimes show you nothing at all. This difficulty becomes especially obvious when dealing with space-time itself. Because space-time provides the structure in which everything happens, it hides behind the events it organizes. It shapes motion, directs light, and determines how time flows, but it doesn't emit light or leave obvious marks. You can't point to spacetime on its own. You can only infer its presence by watching how objects behave inside it. That means that whenever something unusual happens in spacetime, understanding it requires interpreting indirect clues rather than observing it head-on. And the more extreme the conditions become, the more the clues fade until you reach a point where you're looking at the universe through a layer of uncertainty that refuses to lift. One of the most familiar places where this challenge shows up is inside black holes. You can't see the interior because no information escapes beyond the event horizon. Even light, the fastest messenger in the universe, cannot outrun the curvature. If you were outside the black hole watching an object fall in, the object would appear to slow down and dim until it essentially froze in place right at the horizon. But that's only how it looks from your vantage point. The object itself would continue falling inward without noticing the moment it crossed. Its viewpoint and yours diverge completely, and because the interior becomes invisible, scientists must rely on mathematical predictions rather than direct observation. This makes the interior one of the most inaccessible regions imaginable. Another place where invisibility becomes an obstacle is in the early universe. The first moments after the Big Bang were so dense and so hot that light couldn't travel freely. It bounced off particles in a dense fog of matter and radiation. Any direct view of that early period is blocked. The light from that time only became free to travel hundreds of thousands of years later, once the universe had cooled enough for atoms to form. This freed light still exists today as the cosmic microwave background, but it doesn't show the earliest times. It shows a snapshot after the universe had already expanded significantly. So the era where quantum mechanics and gravity both operated at full strength remains hidden. Models can describe it. Mathematics can trace the patterns. But direct observation is impossible. Dark matter creates its own form of invisibility. Galaxies rotate in ways that imply far more mass than the visible matter can account for. Galaxy clusters move as though pulled by an unseen gravitational structure. The bending of light around clusters reveals mass that emits no radiation at all. Every piece of evidence points to a substance that has mass, shapes geometry, and interacts gravitationally, but does not emit, absorb, or reflect light. Since dark matter doesn't interact with electromagnetic radiation, you can't see it in the traditional sense. And because it doesn't collide with ordinary matter in noticeable ways, you can't touch it or detect it directly with current instruments. You only know it's there because the things you can see behave as though something invisible is influencing them. Dark energy is even more elusive. You know it exists because the universe is expanding at an accelerating rate. That acceleration means something is causing spacetime to stretch faster over time, but the something can't be observed. It doesn't form structures. It doesn't radiate. It doesn't cluster. It doesn't behave like any known force. It acts everywhere uniformly, yet refuses to reveal any specific form. Scientists infer its presence through indirect measurements of the expansion rate and through comparisons of observed patterns with theoretical models. But dark energy remains invisible not just visually but conceptually too. It doesn't fit neatly into any existing framework. It's an unseen influence shaping the larger scales of the universe. Quantum fluctuations add another layer of invisibility. At extremely small scales, particles and fields behave unpredictably. They pop in and out of existence. They fluctuate in ways that cannot be pinned down. These fluctuations influence the universe, but they do so at scales too tiny to observe directly. Instead, their presence is inferred indirectly through small shifts in energy levels or subtle patterns in field behavior. You never see the fluctuations themselves. You see their consequences, and because the consequences are often faint, isolating them requires enormous precision. Even the curvature of space-time itself isn't visible. You can't look at a region of the universe and see the curvature directly. You can only see how objects move within that curvature. If light bends around a galaxy, the bending gives you information about the shape of the geometry. If clocks tick differently near a massive object, the timing difference reveals how time is influenced by curvature, but the curvature remains hidden behind the behavior it causes. The geometry doesn't announce itself. It remains silent, always present but never directly detectable. Measurement tools also become part of the problem. If you build an instrument to detect gravitational waves, the waves stretch and compress the instrument itself. The entire apparatus becomes part of the signal. You're measuring something that changes the very tools used to measure it. That creates a situation where the thing you're trying to detect refuses to give you a stable reference point. The slightest vibration, the tiniest shift in curvature, becomes a source of noise or distortion. It's incredible that instruments like LIGO can measure gravitational waves at all. They detect changes smaller than the width of a proton, yet even these measurements rely on indirect inference, because the waves themselves are not visible. Then there are the regions of space-time that are inaccessible simply because of distance. The speed of light limits how far we can see. The expansion of the universe pushes distant galaxies beyond the reach of their own light. Even if the universe continues infinitely, we will always see only a finite region. That means vast portions of the universe remain invisible forever. Nothing from those regions can reach us. They exist beyond our cosmic horizon, unseen and permanently hidden. Their behavior could be similar to what we observe locally, or it could differ in ways we can never confirm. Our knowledge is inherently restricted by the nature of space-time itself. These limits become even more pronounced when you consider that many cosmic structures disappear from view as the universe expands. Over time, as galaxies move farther apart, some will cross the boundary where their light cannot overcome the expansion. They will still exist, but they will no longer be visible. The universe grows more isolated as this happens. The edges of what we can observe shrink relative to the entire universe. Future observers, billions of years from now, might see a sky with fewer galaxies. The clues we rely on to understand space-time will gradually fade as cosmic expansion carries objects out of reach. Another challenge arises from the simple fact that looking far into space means looking far into the past. Light takes time to travel. When you observe a distant galaxy, you see it as it was billions of years ago. You cannot see its current state. That means the visible universe is a patchwork of different eras. Some galaxies appear as they were in the early stages of formation. Others appear in mature stages. Some might have already collided or transformed in ways we will never witness. The present-day universe remains partially hidden because the light from those regions hasn't reached us yet. This time delay complicates efforts to understand space-time evolution. You can see pieces of the puzzle, but the pieces come from different times, making it difficult to form a coherent picture. Observing the universe becomes like watching a movie where the scenes are out of order and many scenes are missing. You can piece together the storyline, but the full picture remains inaccessible. The invisibility extends to the structure of space-time at the smallest scales too. If space-time has a granular or quantum structure, the granularity would be far too small to observe. You would need energy levels so high that trying to observe them would collapse the region you were trying to examine. Anything that extreme produces gravitational effects strong enough to distort or hide the information. The very thing you're trying to see would disappear as you approached it. This creates a barrier preventing direct observation of the smallest scales. Even the shape of the universe as a whole remains hidden. The observable region might look flat, it might look curved, but that visible patch is not the entire universe. It's only what light has been able to show us. Beyond that boundary, space-time could curve differently. It could take on shapes that defy our current models. But because we cannot see beyond the cosmic horizon, those possibilities remain speculative. The true shape could be infinite, finite, looped, open, closed, or something we haven't imagined. The clues we have are weak compared to the vast regions that remain unseen. The trouble with trying to observe the unseen becomes even more apparent when considering the behavior of energy and vacuum fluctuations. The vacuum of space is not empty. It teems with activity at the quantum level, but because the fluctuations happen so quickly and at such small scales, instruments cannot capture the underlying motion. Instead, experiments detect averages or effects integrated over time. That means the true nature of the vacuum is hidden behind statistical behavior. The raw fluctuations remain invisible. Another invisible layer comes from the limitations of human perception. Our senses evolved to navigate environments filled with solid, visible objects on Earth. They didn't evolve to detect curvature or fluctuations or exotic fields. Even when instruments reveal these things indirectly, Interpreting the results requires mathematical translation. The true nature of what's happening remains outside our intuitive reach. We rely on equations, not sight. We rely on inference, not direct experience. That creates a permanent gap between what the universe is and what we can observe about it. This gap doesn't mean the universe hides out of malice. It simply means that the tools available to living beings in a universe governed by relativity and quantum mechanics are limited by those same laws. Light takes time to travel. Gravity bends paths. Quantum uncertainty restricts measurement. Expansion stretches distances faster than information can cross them. All of these constraints shape the ways we interact with reality. Even the structure of time creates invisibility. You can't see the future. You can't directly observe what hasn't happened yet. Predictions rely on theories, and those theories rely on measurements from the past and present. Whether space-time will continue expanding at the same rate, whether dark energy will change behavior, whether the geometry will shift over unimaginable timescales. All of these things lie outside direct observation. The universe reveals its past to us through light and motion, but its future remains hidden behind a veil of possibilities. This accumulation of invisibilities, black hole interiors, early universe conditions, distant cosmic regions, dark matter, dark energy, vacuum fluctuations, quantum scales, true cosmic shape, future evolution, creates a landscape where understanding requires reaching far beyond what can be seen. Every major theory in physics tries to fill the gaps. Relativity handles the large-scale behavior, quantum mechanics handles the small-scale behavior, cosmology bridges the early universe, astrophysics interprets distant light. But each field relies on clues rather than direct evidence. There's a point in this exploration where the questions stop feeling like they're aimed at the universe and start feeling like they're aimed at us. Up to now, it has been natural to treat space-time as something the universe provides, an ingredient we accept as part of the background. It feels like the kind of thing that should exist whether or not anyone is around to think about it, the way gravity works or the way light travels. But once you spend enough time looking at the pieces that don't fit together and the clues tucked into the places we cannot see, the question naturally shifts. You begin to wonder whether space-time is actually the basic fabric of reality, or whether it's something we constructed as a framework to make sense of the world. Not a fabrication or a mistake, but a model built around the conditions we can observe, shaped by the limits of what our senses and instruments can detect. That possibility opens the door to another way of seeing the universe, one where space-time isn't the foundation but a layer of description resting on something deeper. What makes this question interesting isn't the idea that space-time might not be real, it's the idea that it might not be fundamental. Something can be completely real while still being secondary to something else. Temperature is real, but it's not fundamental. It emerges from the motion of particles. Pressure is real, but it's composed of forces between molecules. Even something like colour, which feels intuitive, is an interaction between certain wavelengths of light and biological mechanisms. In each case, the phenomenon is real and useful, but it isn't a building block. It's the behaviour of something else expressed through different scales. When physicists consider whether space-time is fundamental or emergent, they mean something similar. They're not questioning whether space-time exists in the ordinary sense. They're asking whether it's the most basic level of description, or whether its geometry, its curvature, and its properties arise from deeper interactions we haven't yet identified. If space-time turns out to be emergent, then the smooth curves, the bending near massive objects, the stretching of cosmic expansion, and the flow of time itself could all be the result of hidden structures shaping the universe behind the scenes. One of the first motivations for asking this question comes from the difficulties we face when trying to merge relativity and quantum mechanics. When two theories work beautifully on their own, but collapse into contradictions when combined, it often means the common layer we assume they share is the wrong one. If space-time were fundamental, then both theories should connect naturally through it. But they don't. They treat space-time in incompatible ways. Relativity lets it bend and stretch. Quantum mechanics relies on fixed backgrounds and doesn't bend its version of time and space. That mismatch hints that space-time might be a convenient model, but not the ultimate structure. The behaviour of quantum entanglement reinforces this suspicion. Entanglement creates connections between particles that remain coordinated regardless of distance. These connections don't weaken over light years. They don't care about the geometry of space-time. They seem to obey rules that operate independently of distance entirely. Some physicists have suggested that entanglement might be more fundamental than geometry. In other words, the connections between quantum states might give rise to the structure of space-time rather than the other way around. If that's true, then space-time could be a product of relationships between quantum systems, not an ingredient of reality by itself. This idea gained more attention when scientists noticed something surprising in the mathematics of quantum fields and black holes. Some models showed that the surface area of a black hole's boundary encoded information about the interior. The amount of information that could fit inside the black hole wasn't proportional to its volume but to its surface. This was the opposite of what you'd expect from ordinary three-dimensional space. In everyday experience, the amount of information you can pack into something depends on the space inside it. But in these extreme regions, the information seemed tied to a surface instead. That suggested a new way of thinking about reality. Maybe the three-dimensional world is a kind of projection of information stored on a two-dimensional boundary. Not an illusion, but an emergent structure that comes from something with fewer dimensions. That idea led to the concept sometimes referred to as holographic descriptions of the universe. It's not a claim that we live in a hologram in the science fiction sense. It's the idea that space-time and the objects within it might arise from deeper information encoded in a different kind of structure. In that case, space-time wouldn't be the most basic layer. It would be a higher-level behaviour emerging from something more abstract but more fundamental. This remains a theoretical possibility rather than a confirmed description. But the fact that the mathematics works in certain models suggests that our usual picture of space-time might be too limited. Another reason to wonder whether space-time is emergent comes from the behaviour of gravity. If gravity is actually the curvature of space-time, then it isn't a force in the same sense as electromagnetism or the strong force. It's a geometric effect. But if geometry is emergent, then gravity would be emergent too. Some scientists have explored this idea and found hints that gravitational behaviour can arise from statistical processes, much like temperature arises from countless molecules moving chaotically. In these versions, gravity becomes a large-scale effect created by underlying microscopic interactions. The geometry we see is the average behaviour of some deeper system. Even if none of these ideas turn out to be correct, the mere fact that they're plausible suggests that space-time might not be the bedrock we once thought it was. Instead of being the fabric everything is built from, it might be a layer of description that becomes accurate only when we look at the universe at a certain scale. At larger scales, geometry becomes smooth. At smaller scales, if space-time is emergent, the smoothness would dissolve into something more granular or more abstract. That would match the difficulties encountered in trying to measure extremely small distances. The universe resists being examined below a certain threshold, as if the concept of distance itself breaks down once you reach that level. Another way to approach the question is to consider how essential space-time is to our understanding of motion and location. Human experience naturally depends on spatial relationships and on the flow of time. The brain evolved to navigate a world where these concepts are indispensable, but whether those ideas reflect the deeper structure of reality is another matter. Our minds shape the models we build. The models shape our understanding. It's entirely possible that space-time is the structure we noticed first, because it's the one we can perceive most directly. But a deeper structure might be responsible for creating the familiar properties of distance, direction, duration, and causality. There's also the issue of what counts as real in physics. Many things once thought fundamental turned out to be composite. Atoms were once considered indivisible. They turned out to be made of protons, neutrons, and electrons. Protons and neutrons turned out to be made of quarks. Space could follow a similar pattern. What appears continuous and solid at one scale might break down into more fundamental pieces at another. Those pieces might not resemble geometry at all. They could be algebraic structures, networks of connections, information patterns, or something entirely outside current imagination. When physicists explore these possibilities, they often rely on mathematical consistency rather than direct observation. The absence of experimental access to extremely small scales forces them to use theory to explore what might lie underneath. Some approaches imagine space-time as a network of discrete nodes connected in specific patterns, where geometry emerges when many nodes behave together. Other approaches imagine space-time arising from entanglement patterns in quantum states. Yet others treat space-time as something that appears only when certain symmetries break. These ideas differ dramatically, but they share one feature. None of them treat space-time as the root layer of reality. All of them propose ways it could arise from something simpler or more fundamental. Another clue comes from the way time behaves differently in different theories. In relativity, time is part of space-time and depends on gravity and motion. In quantum mechanics, time isn't tied to geometry. It sits as an external parameter that moves forward at a steady rate. If space-time were fundamental, you would expect a single, unified treatment of time, but the universe doesn't present one. This discrepancy suggests that time might not be the foundation of reality. It might instead be something that emerges when certain conditions arise. If time emerges, then space-time cannot be fundamental either, because space-time includes time as one of its dimensions. Even the expansion of the universe raises questions. If space stretches, what exactly is stretching? If space-time were fundamental, the answer might be straightforward. But if space-time emerges from something else, the expansion becomes the behavior of a deeper system, responding to some underlying rule. The accelerating expansion caused by dark energy could then reflect properties of that deeper structure, not properties of space-time itself. In that case, dark energy wouldn't be a mysterious component of space-time. It would be a sign that space-time is only one of the layers shaped by the deeper rules. Another idea that drives the question forward is the fact that many attempts to unify physics remove space-time from the basic starting point. In string theory, the fundamental objects aren't points in space-time but vibrating strings whose interactions produce space-time. In loop-based approaches, space-time is quantized and emerges from discrete structures. In information-based approaches, space-time arises from entanglement patterns. In causal set theory, space-time emerges from networks of events ordered by causality. In each case, the idea of space-time appears later in the theory, not at the beginning. This placement suggests that space-time is a high-level structure, like the surface of water, which appears smooth, even though its underlying components are not. This doesn't diminish the importance of space-time, it simply reframes it. Just as water still exists even though it's made of molecules, space-time would still exist even if it's made of something else. It would remain the environment where planets orbit, where light travels, where galaxies evolve, and where time moves forward. But it would no longer be the deepest truth. It would be something that forms when deeper elements arrange themselves in particular ways, something that reflects larger-scale behavior rather than fundamental nature. What makes this possibility so intriguing is that it aligns with many of the places where relativity and quantum mechanics disagree. If space-time is emergent, then the contradictions between the two theories might stem from using a model that works perfectly in one domain but not in another. Relativity describes the emergent geometry well when the scale is large. Quantum mechanics describes the underlying structure well when the scale is small. But when you try to push relativity into the domain of quantum mechanics, it reaches its limits because it's describing something that no longer exists in its usual form. And when you push quantum mechanics into regions governed by curved geometry, the model breaks because it doesn't account for the emergent nature of that curvature. All of this leads to the larger idea that space-time might be a bridge rather than a foundation, a bridge between the deeper rules and the observable universe, a bridge between the hidden structures we can't see and the physical behavior we can. And the existence of that bridge could explain the mismatches, the paradoxes, the infinities, and the puzzles that appear throughout physics. There's a certain kind of anticipation that comes from standing close to an answer without being able to step all the way into it. Scientists reach that point often, especially when dealing with the deeper structure of the universe. You build a theory, test it, refine it, push it as far as possible, and sometimes it performs almost perfectly. It explains nearly everything you throw at it. It predicts new things with remarkable accuracy. It becomes the lens through which generations look at the universe. Yet there's always a moment, especially in fundamental physics, where you stretch that theory just a little too far and watch it begin to strain. The surface starts to crack. Numbers stop lining up. Patterns begin to blur. It becomes clear that the theory that almost explains everything has a boundary of its own. This is where many of today's ideas sit. They do an impressive job describing enormous ranges of physical behavior. They shape the way we understand nearly every part of nature. But when you place them next to the biggest questions, especially the ones that involve combining quantum mechanics with gravity, they fall just short. They offer partial answers but no complete picture, and that near-miss quality becomes one of the most intriguing parts of the search for a deeper understanding of space-time. The most established example is the pair of theories people rely on every day, general relativity and quantum mechanics. Each one explains a huge part of the universe. General relativity handles gravity, cosmic expansion, black holes, and the curvature of space-time. It's precise, elegant, and astonishingly predictive. Quantum mechanics handles particles, forces, fields, and the probabilistic behavior that governs matter on tiny scales. It has been tested more thoroughly than any other idea in science. But as accurate as both theories are, they don't join into a single unified description. They come close, and in many places they overlap beautifully. Yet in the regions where both should apply, especially at extremely small scales near intense gravitational fields, they contradict one another. Some theories try to merge them from the top down. Others start from smaller building blocks and work upward. But each approach has struggled because gravity behaves differently from the other forces. Attempts to quantize gravity create equations that explode into infinities. Attempts to describe particles purely in geometric terms fail to capture the restless nature of quantum fields. Even attempts to treat time consistently across both theories run into trouble. In relativity, time depends on motion and gravity. In quantum mechanics, time stays fixed. That mismatch alone becomes a major barrier. One of the earliest attempts to combine everything into a single theoretical structure came from the idea of unification. People noticed that electromagnetism and certain interactions could be described together if they were treated as part of a larger underlying symmetry. This led to the development of theories that combined forces at high energies, showing that the differences between forces might only appear at large scales. At extremely high energies, near the conditions of the early universe, the forces could merge. This idea became known as grand unification. It suggested that the fundamental interactions we see today were once part of a single system. But the theory still didn't include gravity, and it required energies far beyond anything we can reach experimentally. Then there's the standard model of particle physics, a framework that describes the known particles and forces except for gravity. It has been enormously successful. It predicted particles before they were discovered. It explained countless interactions. It organized matter into elegant families and symmetries. But even with all its successes, it leaves major questions unanswered. It doesn't explain dark matter. It doesn't explain dark energy. It doesn't include a mechanism for gravity. It doesn't clarify why the constants in the equations take the values they do. It works brilliantly, but only within a specific range. Another avenue that emerged was the idea of extra dimensions. If space-time had more than the familiar four, maybe gravity behaved differently because it's extended into those additional dimensions. This approach showed that gravity could appear weak in our observable universe if some of its influence leaked into hidden dimensions. The mathematics worked nicely in certain models, making gravity seem small in familiar space but strong in others. But despite the appeal, no direct evidence of extra dimensions has been found. And even if they exist, it remains unclear whether they help unify gravity with quantum mechanics in a complete way. Then came the idea of string theory. Instead of treating particles as points, this theory imagines them as tiny vibrating strings. The type of vibration determines the particle. In that framework, gravity emerges naturally, because one of the vibration modes behaves exactly like the graviton, the hypothetical quantum of gravitational interaction. This was one of the first theories to incorporate both gravity and quantum mechanics without generating uncontrollable infinities. It inspired enormous interest because it created a unified picture of all particles and forces, but it also required extra dimensions, specific symmetries, and structures that haven't been observed directly. And because the strings are so tiny, it's nearly impossible to test the theory experimentally. It remains elegant, promising, and incomplete. Closely related versions of this idea explore the possibility that space-time itself arises from deeper objects called branes, or from fields defined on lower dimensional surfaces. In some cases, the mathematics suggests that the universe we see could be the boundary of a higher dimensional space. In others, the geometry of space-time emerges from networks of quantum states. These concepts provide potential bridges between quantum mechanics and relativity, but they remain theoretical. They almost explain everything, but not quite. Another approach takes a different path altogether by trying to quantize space-time directly. Instead of smoothing space-time into a continuous surface, these theories propose that space-time has a discrete structure at the smaller scales. One example comes from loop-based approaches, where space-time is composed of tiny loops woven together into a network. The loops create a geometry that looks smooth at large scales but becomes granular at tiny ones. This avoids the infinities that appear in other attempts to quantize gravity. It provides a natural explanation for why certain quantities remain finite in extreme regions, but the theory is challenging to test, and while it describes many features of gravity, it doesn't yet unify gravity with the other forces. Another near miss emerges from approaches that treat space-time as a network of events connected by causal relationships. In these models, space-time doesn't exist until events occur. The relationships between events create the geometry. This removes the need to treat space-time as a continuous background, which helps avoid contradictions with quantum mechanics. But turning causal relationships into smooth geometry requires many assumptions, and the connection to observable physics remains tentative. Some ideas approach the problem from the direction of information. Instead of treating space-time as a physical object, they treat it as something that emerges from the way information is stored and shared among quantum systems. In this picture, entanglement doesn't just connect particles, it shapes geometry itself. Distances emerge from how strongly states are linked. Curvature emerges from how information flows. These ideas are mathematically compelling, and they link several puzzling features of black holes and quantum fields. But they're still young. They haven't yet been shaped into a testable theory that explains all known physics. Even inflation, which explains many features of the early universe, has gaps. It describes how the universe expanded rapidly shortly after the Big Bang, smoothing out irregularities and producing the uniformity we observe. It predicts the patterns in the cosmic microwave background and explains why space appears nearly flat. But inflation requires specific conditions to begin. Those conditions aren't explained by the theory itself, and inflation predicts a variety of possible universes depending on the details. That raises the question of whether the theory is describing fundamental physics or just one version of a broader set of possibilities. Quantum field theory, The framework that underlies the standard model also reaches its limits. It describes particles and forces as excitations of fields spread across spacetime. It works extraordinarily well. But when you try to apply it in curved spacetime, especially near black holes or during cosmic expansion, new puzzles appear. The theory suggests that the vacuum isn't empty but filled with fluctuations, but the amount of energy predicted by those fluctuations is far too large. If the prediction were accurate, spacetime would curve violently. But it doesn't. Something about the combination of vacuum energy and gravity refuses to align. Supersymmetry offered another possible extension. It pairs every known particle with a heavier counterpart. If supersymmetry were real, it could solve several problems at once. It could explain dark matter. It could stabilize the vacuum. It could unify forces at high energies. But despite decades of searching, no supersymmetric particles have been found. The idea remains mathematically elegant but experimentally unconfirmed. Then there's the ongoing puzzle of dark matter itself. Some theories propose that dark matter is made of undiscovered particles. Others suggest that gravity behaves differently on large scales. Modified gravity theories attempt to explain galactic rotation without invoking dark matter. These theories produce interesting results, especially in specific systems, but they struggle to explain all the evidence consistently. They almost explain everything, but not quite. Even the idea of unifying all forces into a single framework encounters obstacles. Each attempt requires conditions that may not exist in reality, or relies on energies we cannot access. And when trying to push these theories into regimes where quantum mechanics and gravity collide, the mathematics becomes tangled. The theories predict particles we haven't found or behaviours that conflict with observation. Their beauty often comes from mathematical consistency rather than empirical success. These near-miss theories reveal something deeper. The universe isn't failing to provide a final answer. The theories are showing where their strengths and weaknesses lie. Each one captures a part of the picture. None captures all of it. That suggests that the truth might lie in a combination of ideas rather than a single, tidy solution. Or it could mean that the next breakthrough requires a completely new viewpoint, something that reframes space-time and its relationship to matter, energy, and information. Despite their limitations, these theories guide scientists closer to the point where the missing piece might appear. They reveal patterns that repeat across different models. They show which features are essential and which are artifacts of the mathematics. They teach researchers where contradictions arise and where assumptions no longer hold. There comes a point in any long exploration where the questions begin shifting their tone. They stop feeling like puzzles to be solved and begin feeling like invitations to look more closely, like gentle reminders that understanding isn't always about reaching the end of something. In physics, especially the physics dealing with space-time, quantum behavior, and the nature of reality itself, that shift arrives quietly. You spend so much time following theories that nearly work, examining ideas that come close to explaining everything, and trying to resolve contradictions that refuse to settle, that eventually the path ahead becomes less about what is known and more about the landscape of possibilities spreading out in front of you. It becomes a place where uncertainty isn't a roadblock but a guide, steering you toward areas that might reveal something new. One of the first things you notice when thinking about the future of physics is that it rarely moves in straight lines. Each major idea from the past century emerged not as the next obvious step, but as something that surprised almost everyone who encountered it. Relativity rewrote the rules of space and time. Quantum mechanics shattered any notion of predictable certainty. Cosmology revealed that the universe was expanding. Dark matter hinted at invisible mass-shaping galaxies. Dark energy introduced a force stretching space-time in ways no one had expected. None of these discoveries lined up in a tidy sequence. They emerged from experiments, mathematical questions, or contradictions that forced people to look beyond familiar assumptions. So when you imagine what the future might hold, the safest expectation is that it won't follow the patterns we currently consider natural. The challenges that lie ahead are immediate and deep. The tension between quantum mechanics and gravity remains unresolved. The nature of dark energy is still an open question. The identity of dark matter is unknown. The early universe hides behind a curtain of opacity. Black hole interiors remain inaccessible. The quantum structure of spacetime, if it exists, has not yet been detected. Each of these issues points toward a gap in our understanding, suggesting the existence of something more fundamental waiting beneath the surface. But none of these gaps tell us clearly what direction to take. They only indicate the boundaries of what our current models can handle. One possibility for the future involves building a theory that unifies everything into a single coherent framework. People have been trying to do this for decades. The appeal is obvious. If the laws of nature arise from a common foundation, then the mismatches we see today could be resolved naturally. A unified theory would describe gravity and quantum mechanics together, explain the origin of space-time, reveal the nature of dark matter and dark energy, and provide a consistent picture of the early universe. But the difficulty lies in the fact that each step towards such a theory introduces new complexities. The mathematics becomes harder to interpret, the physical implications become more abstract, and the distances between prediction and observation grow wider. Even so, the search continues because the match between patterns across different areas hints that unification remains a reasonable goal. Another possible direction comes from the idea that the universe might be understood better through information than through matter or fields. Information-based approaches propose that everything in the universe, including space-time, arises from underlying informational processes. Entanglement, causality, symmetry, and probability become the fundamental ingredients. Geometry emerges not from physical objects but from the way information is structured and shared. Put this way, the universe becomes something like a network of relationships, where the shape of space-time reflects the strengths and weaknesses of those relationships. If this path leads to a deeper theory, it could explain why entanglement plays such an important role, why black hole information behaves the way it does, and why space-time seems flexible rather than rigid. There are also approaches that imagine the future of physics requiring an entirely new conception of time. Right now, time is treated differently in different theories. In relativity, it is a dynamic dimension woven into space-time. In quantum mechanics, it is an external parameter that moves forward at a steady rate. This mismatch might be hiding something important. Some future theory might reveal that time is not fundamental at all, but something that appears only in certain conditions. Perhaps time is emergent, arising from statistical patterns, entanglement structures, or deeper symmetries breaking at large scales. If this turns out to be true, the flow of time could be more like the flow of temperature or pressure, not a basic property of reality, but a behavior that emerges from many interactions working together. There's also the possibility that the universe contains structures or objects we haven't discovered yet, ones that don't fit into any of the categories we've established so far. When scientists talk about dark matter, they often assume it will eventually be identified as a particle. But it could be something entirely different, such as a new kind of field, a modification of gravity, or a sign that the structure of space-time changes at large scales. Dark energy might not be a form of energy at all, but a sign of some larger process shaping the geometry of the universe over time. These unknowns hint that the future might involve rethinking the categories we take for granted. Another direction might come from studying the smallest possible scales more closely, not through direct measurement, but through theoretical advances that reveal how space-time behaves when distances shrink far below what we can observe. At those scales, quantum fluctuations could dominate. Geometry could dissolve into something unpredictable. Distances and durations might no longer have meaning in the traditional sense. The familiar picture of space-time might be replaced by something more discrete, more dynamic, or more relational. If this happens, many of the contradictions between relativity and quantum mechanics could resolve themselves naturally. The apparent incompatibility might stem from trying to describe smooth geometry in conditions where smoothness breaks down. There's also a growing sense that the next major breakthrough might come not from physics alone, but from mathematical structures that have not yet been applied to physical theories. Many past discoveries emerge from mathematical insights that didn't initially appear connected to physical reality. Non-Euclidean geometry seemed purely theoretical until it described curved space-time. Complex numbers seemed abstract until they explained quantum wave functions. Group theory seemed esoteric until it organized the symmetries behind fundamental particles. Today, there are entire areas of mathematics that haven't yet found their physical application. As more ideas intersect, the future might involve structures that make the behavior of space-time, quantum fields, and cosmological evolution look like natural consequences of a deeper mathematical environment. There's also the possibility that the future will require a shift in perspective rather than new equations. Humans naturally imagine the universe in spatial terms. We rely on visual thinking, intuitive geometry, and spatial relationships to make sense of the world. But space-time at the smallest or largest scales might not behave in ways that match those intuitions. The future might demand thinking in ways that don't rely on familiar concepts. This could mean visualizing reality as something more network-like or process-based. It could mean focusing on relations rather than objects. It could mean understanding fields not as substances filling space, but as manifestations of deeper layers we haven't conceptualized yet. Even the idea of causality may be revisited. In everyday life, cause leads to effect in a straightforward chain, but quantum mechanics challenges this simplicity. Some processes appear to lack a clear order. Entangled states behave as though they share information outside of ordinary causal chains. In some theoretical frameworks, causality itself emerges from deeper principles rather than existing as a foundational rule. If the future reveals that causality is not an absolute structure, but one that appears only in certain regimes, it could change how we model the universe at every level. Observational advances will also play a significant role in shaping the future of physics. New telescopes, detectors, and instruments will provide data from regions previously inaccessible. Gravitational wave observatories may grow more sensitive, capturing waves from the early universe or from objects that test the limits of relativity. Particle accelerators might discover new particles or rule out entire classes of theories. Space-based detectors may reveal subtle shifts in cosmic expansion or uncover patterns in gravitational fields that point toward new physics. Each new piece of data becomes a stepping stone toward whatever theory comes next. But even with better technology, the universe imposes limits. We can only see as far as light can travel. We can only measure as deeply as quantum uncertainty allows. We can only infer structures that produce observable effects. Large portions of reality may remain forever beyond our observational reach, yet even those limits can help guide theory. They tell us where the gaps lie, they reveal where the models begin to falter, and they show us the types of explanations that might work across those boundaries. Another important shift in the future might involve accepting that some questions do not have single, straightforward answers. The universe might not be built from a single unified structure. It might be composed of layers, each with its own rules, each emerging from the one beneath it. Space-time might emerge from quantum processes. Quantum processes might emerge from symmetries. Symmetries might arise from even deeper patterns. And those patterns might not resemble anything we consider physical in the traditional sense. If this layered view becomes central, the future could focus on understanding how each layer connects to the next, creating a more flexible picture of reality. Thinking about the future of physics also means accepting that some of the ideas currently considered fringe or speculative might become mainstream. Many revolutionary ideas began as speculative. Quantum mechanics was once controversial. Relativity was once considered radical. The expansion of the universe was once doubted. Theories that seem unconventional today could become the foundation of tomorrow. Their current limitations don't necessarily reflect flaws. They might simply reflect the early stages of development. Just as likely is the possibility that the next breakthrough will come from recognizing a pattern hiding in plain sight. Something simple yet overlooked because it doesn't fit the expectations shaped by current theories. Many advances in physics came from small clues that didn't seem significant at first. The slight anomaly in Mercury's orbit led to relativity. The ultraviolet catastrophe led to quantum mechanics. The faint uniform glow of the cosmic microwave background reshaped cosmology. The future might depend on noticing something equally subtle. There's also an emotional aspect to imagining what comes next, a sense of being part of a long process that extends far beyond any single lifetime. Every scientist contributes a small piece. Every measurement adds a fragment. Every idea, even the ones that don't survive, nudges the collective understanding in some direction. The future of physics is not a competition to reach a final answer, but an ongoing collaboration with the universe itself, observing, asking, testing, adjusting, and slowly revealing more of what lies beneath. And as these questions keep expanding, as the theories keep reaching toward deeper possibilities, the path ahead stays open, allowing the exploration to continue.